Our hearts beat to the city streets. We began to feel the fire. We rise like tall buildings as the chemicals, they take us higher. The night's young and it's just begun as she puts her hand in mine. We wanna chase the night, wanna dance to the light, pull stars from the sky, just two hearts running wild. Never sleep, never stop, as we shout from the top. We're gonna be two hearts running wild. So loud as the hours pass, we're gonna do it all again. We wanna chase the night, wanna dance to the light, pull the stars from the sky, just two hearts running wild. Never sleep, never stop, as we shout from the top. We're gonna be, we're gonna be two hearts running wild. The moonlight, summer sky, it was the best we ever had. And we'll stay on forever, we'll never have regrets. We wanna chase the night, wanna dance to the light, pull the stars from the sky, just two hearts running wild. Never sleep, never stop, as we shout from the top. We're
I am very happy to be present on this day since it's the mark of the 65th founding anniversary of KMUTNB. My name is Nisha Davis and I will be your MC throughout the morning session. On the behalf of King Mongkut University of Technology, North Bangkok, and other committee members, we wholeheartedly welcome you all to the International Conference on eco-friendly fibers and polymeric materials, EFPM 24. On this memorable occasion, we are very happy to telecast a video of our prestigious KMUTNB. So please enjoy.
KMUTNB's 64th anniversary Innovation Pathways towards Sustainable Technology. From the practice of the new normal habits after COVID-19 to life and work in the era of the next normal, people's lifestyles have been transformed to adapt to science and technology-driven lifestyles that are changing at a rapid pace. It is necessary to delve into sustainable technology innovations that are critical to the future well-being of society and support the sustainability agenda. King Mongkut University of Technology North Bangkok, or KMUTNB, was founded on February 19, 1959 as an academic institution for education-economic cooperation framework between the German and Thai governments. It was initially called North Bangkok Technical School and was generally known as Thai-German Technical School due to its implementation of the German dual system of vocational training that showcases work-based and theory-based education. The name King Mongkut University of Technology was derived from the name of His Majesty King Mongkut, or Rama IV, while His Majesty's Royal Grand Crown Seal is taken as the university's emblem. His Majesty, the late King Bhumibol Adulyadej, graciously granted the university the privileges to use them as the official name and logo. Currently, KMUTNB is an autonomous university of invention to innovation. The university offers courses at different levels of education, covering the vocational certificate, bachelor's, master's, and doctorate degree programs. KMUTNB has expanded educational opportunities to students in different regions. KMUTNB, Prachinburi and KMUTNB Rayong campuses were founded to encourage business industry expansion in Thailand's Eastern Economic Corridor, or EEC. The education provided plays an important role in empowering students and faculty toward technological advancements, research and development, and innovations. Talent development and the power of self-reliance foster engagement and participation in national and global competitions. KMU-TNB has multiple academic collaborative networks with national and international public-private corporations and industries. The main purpose of strategic alliance networks is to further expand the body of knowledge which would help individuals to build their competence towards research and technology leadership in the framework of university-industry collaboration. KMU-TNB encourages adherence to good governance practice through transparency and accountability. The university has achieved prestigious awards in recognition of excellence in corporate governance. Throughout 64 years, KMU-TNB has shown great commitment to the development of human resources alongside the advancement of science, technology, and innovation. Innovation and technological progress will drive Thailand's economy and way of life to sustainable technology implementation. The vision of contributing to a sustainable future through technology and innovation plays a role in supporting KMU-TNB towards becoming a leading and internationally recognized academic institution in science, technology, and innovation.
So you have noticed that the starting of the video is the 64th anniversary. So for the newest one, we will be showing at the evening reception. So we would like to all of you to join us for the evening session, party and celebration also. So in this part, I'm really happy and welcome our beloved President, Professor Dr. in Habilitation Suchat Singh Chin for delivering the presidential address via the video presentation.
วิดีโออาจารย์สุชาติที่บอกใช้เป็นสปริงเกอร์ On behalf of King Mongkut University of North Bangkok, dear distinguished guests, ladies and gentlemen, good morning everyone. On behalf of King Mongkut University of North Bangkok and myself, we are greatly honored and pleased to welcome you all to the International Conference on Eco-Friendly Fiber and Polymeric Materials. On the occasion of 65th year anniversary of KMU-TNB, I would like to begin by thanking the keynote speakers, Professor Dr. Mohammed Jawai from United Arab Emirates University, Professor Dr. Silam Ramakrishna from National University of Singapore, Professor Dr. Home Dhaka from University of Portsmouth, United Kingdom, and Professor Dr. Yotish Kumar Paramesh Valampillai from Orange University, India, for gracing us with your presence today. Let me also take this opportunity to thank our invited speaker for the effort and believing in the cooperation with KMUTNB this year conference. The King Mongkut University of North Bangkok is one of the largest technical universities in Thailand and was established from the constructive cooperation between the Thai government and Federal Republic of Germany. It was initially known as the Thai-German Technical School, whereas the objective was focused on the production, highly skilled technician and engineering for Thailand. Our success is reflected by the German teaching style and has embedded in the most of vocational college throughout the country. To expand the King Mongkut University of North Bangkok capacity and the occasion of 65th year anniversary of KMUTNB, we are organizing the International Conference on the Eco-Friendly Fiber and Polymeric Materials, aims to focus on the exchange relevant trends and research results, as well as the practical presentation and research experience exchange in eco-friendly materials. Your scientific contribution in this conference are valuable source for other researchers and educators to study. I hereby acknowledge and appreciate the efforts and cooperation of everyone for project cooperative arrangement and coordinators. Thank you so much for coming and for your attention. So please enjoy the conference. Have a good day. Thank you very much.
Thank you very much to President. Due to the obligations of today's event, he sent his best regards and he will be joining us later today. Next, I feel immense pleasure in welcoming the Vice President of Research and Information Technology Development of KMUTNB, Professor Dr. Sumrak Chantra Amphorn, for delivering a facilitation. Please welcome on the stage.
Good morning, everyone, and I will say welcome to you very short because what is in my head is quite similar to the one the President have said. Okay, ladies and gentlemen, on behalf of King Mongkut University of Technology North Bangkok, I would like to welcome you all to Thailand and to Bangkok and to our university, King Mongkut University of Technology North Bangkok, or KMUTNB. And I think we all know well that now we are moving to the more sustainable world, and the research in this domain in eco-friendly materials is really important and plays the important role on achieving this goal. So I would like to say that you all in this room are very important persons to do the research for the more sustainable world, and I would like to thank you very much. And as for our UC KMUTNB, I would like to say that our university was established about 65 years ago, and we emphasize in engineering and technology. And one of the research area that we can do very well is a field of materials. And I think this event is also a part of our celebration of the 65th anniversary of our university. And in this occasion, let me thank again our keynote speakers from UK and from UAE, from India and from also Singapore. And I would like to thank the participants, the presenters and the audience, both on-site and online, about 140 people. And I do hope that by joining this conference, you will gain more knowledge gain more new idea on new friends and also new networking. So in this occasion, let me declare the opening of the conference and let's enjoy this event. Thank you.
Thank you very much, the Vice President, for your facilitation. We are very much happy in introducing our Natural Composites Research Group Laboratory through a short video presentation.
Natural Composite Research Laboratory was established in 2011 under the Department of Materials and Production Engineering. The Sirindhorn International Thai-German Graduate School of Engineering, King Mongkut's University of Technology North Bangkok, Thailand. NCR Lab's prime focus is on applied research related to the development of natural fibers, their composites, polymeric materials, polymer blends, rubber technology.
excuse us, we adjust the schedule a little bit because we now have the president of KMUTNB to joining us for the event this morning. So at the moment, I would like to invite our beloved president, Professor Dr. Ing Habilitation Suchat Sieng Chin, to present the mementos for the keynote speakers on the stage, please. Yes, we will move the podium away a little bit. In this part, I would like to invite Professor Hamnath Dakal from University of Portsmouth of United Kingdom to receive the memento, please. We have a couple of mementos. Please stay on the stage. Please, Professor. Because KMUTNB is very appreciate for the keynote speakers to give your time and your knowledge to hear. So we have a couple of the mementos. Thank you very much, Professor Hamnath Dakal. Next, I would like to invite Professor Siram Ramakrishna from National University of Singapore to receive the memento on the stage, please. Thank you very much. Next, I would like to invite Professor Mohammad Javed from UAE University of United Arab Emirates to collect the memento on the stage, please. Thank you very much, Professor. And the fourth keynote speaker, I would like to invite Professor Yotish Kumar from Alliance University, India, to receive the memento on the stage, please. Thank you very much, professors and all keynote speakers for today. And now I would like to invite everyone for the group photo along with the beloved President and the Vice President. Please welcome on the stage. Yes. So we would like to have everybody down onto the front stage, please. Some participants could get on the stage and form the second lines. Please have the fully participants today. And along with us today, we have more vice presidents of the university, the vice presidents for academic affairs and assistant to the president, to join us with the photos of the conference today also. Thank you very much, the vice presidents of KMUTNB, the president, and also the participants of the international conference, Eco-Friendly Fibers and Polymeric Materials. Due to today is the anniversary day of KMUTNB, our president and vice presidents and our executive team of KMUTNB will be walking around the university and have different events that happen and occur today. But you will see them around at the exhibition and also definitely at the evening reception in the evening. So some of our vice presidents and the president will be joining us for a little bit more before his next program and agenda for today's events. As we mentioned, it's a very big day for KMUTNB, and we are very grateful for all participants to have the international conference today with us and also joining us celebrate the KMUTNB 65th anniversary. And for this part, I feel honored to invite Dr. Sanjay Mavenkar Ravakappa, Senior Research Scientist, Associate Professor, and also an advisor within the Office of the President for University, the Promotion and Development towards International, Global, and the Chairman of EFPM 24 to deliver the welcome address, please.
Good morning to everyone. I'm happy to be a part of this event since we are celebrating 65th founding anniversary day of KMUTNB. As I'm the chairman of today's international conference on eco-friendly fibers and polymeric materials, EFPM 24, I'm happy to greet all of you here on behalf of our university and welcome you all for this conference. I wish to welcome you all. First, I would like to thank our beloved chairman of university, Professor Dr. Thiravat Bonasufun, and our beloved president of KMUTNB, Professor Dr. Ing Abel Suchat Singh Chin, director of KMUTNB Technopark, Professor Dr. Pricha Ungeri, for their great support and encouragement to organize this conference. I would like to welcome our Vice President for Research and Information Technology Development, Professor Dr. Sumrek Chandra Amron, and Vice President Professor Dr. Sonit, and our Professor Malini, Professor Sunesh, Assistant to the President, and all keynote speakers and invited speakers and all the participants from various countries. Personally, I welcome and appreciate the keynote speakers, Professor Dr. Amnath Dokal from University of Portsmouth, UK, Professor welcome. Professor Dr. Siram Ramkrishna from National University of Singapore, Professor welcome. Professor Dr. Mohammad Javed from United Arab Emirates University, UAE, Professor welcome. Professor Dr. Jyotish Kumar Parmeshwar Pillai from Alliance University, India, Professor welcome, for accepting our invitation. Also, I would like to welcome and appreciate Professor Dr. Kirtikin from KMUTNB, Professor Dr. Suresh from NIE Mysore, Professor Dr. Viresh Kumar from NIT Andhra Pradesh, Professor Dr. GM Madhu from Ramayana Institute of Technology, Bangalore, Dr. Santil from Kalasingam University, Professor Dr. Jayanti from VIT, Dr. Suganya from CIT, Professor Dr. Elmaran Germany from Swinburne University, Malaysia, Professor Dr. Muhammad Ajit from UTM, Malaysia, Professor Dr. Unko from Namdi Ajikwi University, Nigeria, and Professor Dr. Emuna from Malaysia, and also other invited speakers from India, Nigeria, Malaysia, Thailand for accepting our invitation. And also I would like to welcome and appreciate the support rendered by all the advisory committee and scientific committee members of this conference. Next, I would like to thank Technopark, STRI, ICC, AED, TGS, faculty members, Central Library, and other staff members of Technopark and KMUTNB. I wish to thank AED, National Research Fund, and STRI for funding support. I also sincerely welcome all the members of media who are here to cover EFPM 24. Further, I extend my sincere gratitude to all the participants who are registered for this international conference. I would like to say a few words about our Natural Composites Research Group Lab, NCR. NCR was established in the year 2011 under the Department of Materials and Production Engineering under the Sindron International Thai-German Graduate School of Engineering, TGS. The lab members of NCR work on exploring possible solutions for creating sustainable, eco-friendly materials for industries to minimize and replace synthetic materials. Many industries and academic collaboration projects are being currently carried out in our NCR lab. NCR has a very good track record for publication with 800 plus research and review articles in reputed international journals, 50 plus books with all leading international publishers, several book chapters, editorial corners, and a few international patents. As another feather in the cap of NCR, many of our group members and NCR collaborators are listed in top 2% scientists in the Stanford University list released by Elsewhere from 2019 to 2023. Coming to main theme of this conference, EFPM 24, this conference mainly focuses on the themes such as fibers, biofibers, biopolymers, biocomposites, with different advanced manufacturing methods to reduce synthetic materials from possible eco-friendly sustainable materials. For our conference, we have received more than 200 papers and selected around 140 papers for presentation from various countries, including Thailand, India, Germany, Italy, Indonesia, Malaysia, Nigeria, Singapore, UK, Saudi Arabia, and Turkey. More than 300 authors are involved in contributing their work in EFPM 24 for various countries. Finally, I would like to express my gratitude and thanks to all the team members, Dr. Pinay, Dr. Indran, Dr. Satish, Dr. Manoj, Associate Professor Dr. Kiritin, Associate Professor Dr. Dao, Dr. Vijay, Dr. Vinod, Assistant Professor Dr. Chakapan, Assistant Professor Dr. Dao, Joe, Assistant Professor Dr. Krit, Dr. Divya, Dr. Narayan Swami, Dr. Gokul, Dr. Ritin, Mr. Praveen, Mr. Arul, Mr. Rasugo, and Mr. Dri, and also intern students from India and Malaysia. Also, I would like to thank the University Academic Council, University Conference Committee, and Ms. Siri, Head of the Administrative Office of KMUTNB Technopark, and our team from Technopark, Ms. Stig, Director of ICC, and our team of AED, team of STRI, team of TGS, and Ms. Sunny, Acting Director of CEM, for their support. I would like to thank all the editorial members, editor-in-chiefs of supporting journals, FACTA, FME Transaction, Applied Science and Engineering Progress, Mechanics of Advanced Composite Structures, Reports in Mechanical Engineering, and Springer Proceedings in Materials to accept our request to publish the conference papers. I hope you all will enjoy the speeches by keynote speakers and invited speakers. The participants will definitely gain various insights regarding eco-friendly fibers and polymeric materials from various sessions. Once again, I welcome you all to EFPM 24. Thank you for this opportunity. Thank you, one and all. Thank you.
Thank you very much, Dr. Sanjay Marankappa, for the speech. And for this part, select the time for the keynote speaker session. I would like to invite Dr. Dao, Associate Professor in the Faculty of Engineering, to introduce our first keynote speaker, please.
Thank you, Ms. Honey. Good morning, everyone present here. The first keynote speaker for this conference is Professor Dr. Hamnat Dakal from University of Portsmouth, United Kingdom. Dr. Hamnat Dakal is a full professor of mechanical engineering at the University of Portsmouth, England. He leads as the chair of the Advanced Polymer and Composite Research Group within the School of Mechanical and Design Engineering at the University of Portsmouth. He is a visiting professor of bio-based composite material at the Faculty of Textile Engineering and Business, University of Borås, Sweden, and an honorary chair of Sustainable Biomaterial, Madan Bandari University of Science and Technology, Nepal. His research interest and expertise include the development, testing, and characterization of sustainable bio-based lightweight composite and hybrid composite for advanced engineering applications. His publication track record includes more than 200 peer-reviewed journal articles, including books, book chapters, and conference proceedings. He is listed in world's top 2% most cited scientists by Stanford University and Elsevier ranking in 2022 and 2023. He is an associate editor of Composites Part C and also an associate editor of Helion. He is a collectorate engineer, a member of the American Society for Composites, and a fellow of the Higher Education Academy, the Institution of Engineering and Technology, and the Institute of Material, Minerals, and Mining. I now invite Professor Dr. Hamnat Dakal to deliver his keynote speech on lightweight bio-based composite for advanced applications, key performance targets, challenges, and opportunities. Over to you, Professor.
It gives me immense pleasure to be here, especially on the occasion of 25th founding anniversary of King Mongkut University of Technology, North Bangkok, whom I have been privileged to collaborate and work for the last 6 years. It has been really honored to be here. Especially I would like to thank Professor President Shuchart and Dr. Sanjay for giving me this opportunity, as well as I would like to express my sincere gratitude to the committee for organizing and inviting me in this occasion. Well, I have a lot of things to say. I have 20 minutes to talk about my work, so I rather focus on my work. Yeah, again, wonderful to be here. I think I must say one thing. Looking back your journey from Thai German Technical Institute to one of the universities in the world working in the forefront of sustainable materials is an amazing journey. So I'd like to wish you all the best for your future, and in no time you will be a very popular university in the world working in the sustainable materials innovation and development. Right, with that I would like to just focus on advanced polymers and composite research group, some of the work that we have done, especially bringing sustainable bio-based composite for advanced applications, opportunities and challenges. Quick outline introduction, and I would like to spend a little bit time on what we are doing at the University of Portsmouth within Advanced Polymers and Composite Research Group. Soon this is going to be a center, so which is we are very excited. So if that happens, obviously I will inform. And then obviously bio-based composite performance targets and key application areas. That is the key topic of my talk. And then how we can enhance the performance of these materials, and then conclusion and future perspectives. Well, University of Portsmouth is located south coast of England. It's a beautiful place. We are next to English Channel. So we are TEF Gold University. Our university is evaluated in terms of research, that is called REF, Research Excellence Framework. And in terms of our teaching, it is evaluated by Teaching Excellence Framework. So we have been very fortunate to get TEF Gold status for the last 8 years in this evaluation. So a lot of our graduates are employee ready. So they when they finish their work, study, they go in the market and then they get good jobs. And then we have about 23,000 undergraduate students, total 28,000 students, about 3,000 staff. And then School of Mechanical and Design Engineering, where I belong, is one of the largest schools in the university. So we do have a lot of facilities to do our research. So yeah, some of the companies that we work are these very reputed company. We believe that we need to help industry to tackle their problem, or we tackle problem together, the problem that society is currently facing. So we have recently launched a Revaluation Plastic Institute, where Professor Steve Fletcher, one of my colleagues, leads that institute, and these are some key the work that institute undertakes, and I'm responsible for sustainable reinforced plastic for engineering applications. One of my colleagues, Professor Andy Pickford, he works on enzyme-related work, and recently they have received, this enzyme center has received 100 million sterling to carry on research. So this is just a very, in the hot press, just last week it was announced. So this is very big boost for us to do further research in plastics. So University of Portsmouth is very focused on sustainability aspect of our work. So that is very, very exciting. So as I said, I belong to Advanced Polymers and Composite Research Group. Within the School of Mechanical and Design Engineering. So our focus is developing sustainable materials for engineering applications. So that is what we try to do. Within that, there are so many things come. Obviously, I will be sharing that as I go along. So some of the key work that we are doing, I would like to just share with you. We do a lot of low velocity impact testing because when you develop new materials, your aim could be using for a marine application or automotive application. So these testing are very important. We do work on environmental exposure of these different materials and how these materials behave under different exposure conditions. So that involves seawater immersion, exposed to extreme weather condition, and then how that influences the performance of these materials. We do work on 3D printing of bio-based composite materials, and now we are thinking to move towards 4D printing. So that is quite exciting area again. Then obviously we work on modeling aspect of materials. There you can see on the left-hand side there's some microplastic release of these materials because we are naval city. Portsmouth is naval city, so we have a lot of boat building companies around us. So we have to work with marine-related research. So we do work a lot of marine-related research. So within that, we work on microplastic release of our materials. So when you develop new materials, if you are using for marine applications, what are the release rate and leachate and so on. So this is just the recent paper published that polypropylene and PLA, we are looking how much microparticles are released from this material. Obviously, we also work on the PLA, PHA, these are the biodegradable polymers, and comparing to PBS and polypropylene, and then just looking some results. So we are getting quite good results now from our bio composite. Obviously, we know what is bio-based composite when the reinforcement or polymer, one of them are from biodegradable source. They are bio-based composite. When you say biocomposite, obviously both are biodegradable. So here we are looking PLA, PHA, and flax. So fully biocomposite and getting quite high mechanical performance, which is quite exciting for us. So, yeah, and then obviously imaging of these materials, evaluation and characterization is very important. So this is some of the work that we do within our research group. So just wanted to show some recent work. We are working on jute fiber composite, looking their performance, low velocity impact, mechanical performance, and so on. So just the exciting result that I want to share with you. Our work on the jute fiber composite, we are able to get 176 megapascal of tensile strength and 16 gigapascal of tensile modulus with enhanced fiber architecture and with some advanced treatment technique applied. So that is quite remarkable properties that we can achieve for bio-based composite. So if we can, optimize processing parameters and material parameters, that we can achieve quite a big, performance. Just wanted to share with you. I don't want to dwell too much on this one. Obviously, we're working in natural fiber composite. We all know what are the benefits of these materials and where these materials are available. So you can see here, Thailand must be somewhere for canal fiber. Yes, we can see there. So there is tremendous opportunity for us to work in different types of natural plant fibers. So, well, we also know that there are certain limitations, but I'm a person that I don't worry too much about limitations. We can always, enhance them. So there's no point just complaining there are so many. Obviously, we need to understand what are the limitations in terms of variability, in terms of moisture absorption, how they affect our final performance. It's good to understand that and then work towards that. But that doesn't limit using these materials in advanced applications. There are several opportunities that we can use this material. So I just want to refer, I hope, Professor Javed just wrote recently an email, I don't know, some of you may have received, asking whether you'd like to contribute to his book, and that was banana fiber. Then he wrote me and then asking home, would you like to contribute banana fiber in space application? I thought, oh my goodness, banana fiber in space application. And then I thought, wow, why not? He's the guy, he's the person, he's the living legend who believes that this material can be used for space application. Why not? So I was very challenged and I said yes. So I said yes to, I will be happy to contribute in your book. So that is the attitude I think we have to take. Our mindset. 20 years ago, we are very limited these materials to be used in non-structural application. Yeah, we are so limited ourselves in non-structural applications. Maybe that was true because at that, 20 years ago in natural fiber composites, we are just beginning the journey. But now we have reached that, so much in our research and development. We have now unidirectional fibers. Flux fiber, very high quality unidirectional fibers can be, have been developed. So that gives us tremendous opportunity to work with natural fiber, natural plant fiber composite for advanced applications. So here just I want to give one quick overview. Obviously, again, this is very familiar slide that those who are working in natural plant fibers, the specific properties is very important. If we compare specific properties of flax fiber, for example, with e-glass, is very comparable, even a lot higher than e-glass fiber. So what are the benefits that we can get from this is a big thing. And then when we look the environmental aspect or environmental performance compared to flax fiber and then a carbon fiber and a glass fiber, obviously flax fiber has got far better environmental performance compared to conventional materials. So that also gives us a lot of excitement that these materials are the materials that we need to work further. And they can replace this non-conventional. Maybe difficult to replace fully this material. They also have got amazing attributes like carbon fiber or glass fiber, but there are so many areas that we can replace them. Right, so here I just like to quickly share some of the facilities that we have because that will help us to understand each other. I was so fascinated to see the facility that you have got here in a natural fiber composite research group. That was just amazing, phenomenal. Yeah, so I really admire that. So I just want to share some of the facilities we have got. We have got 3D printing of bio-based composite and metallic materials facilities with us. And we also have got advanced techniques, manufacturing facilities, EDM, wire EDM, water jet cutting, and so on. So these are very good facilities to have in terms of machining and manufacturing. Then we have 3D printing, and then we have got very advanced X-ray microscopy to characterize some of our materials like fibers and fiber architecture and fiber morphologies. Then we have got good characterization techniques, again, different types of SEM available for us. And these are the key application areas or industries that we can take our materials. So this space we can go. We recently applied for funding for space application of flax fiber composite. So sometimes you think that flax fiber for space application. So that is what we have been doing. Obviously, these are the key sectors we can approach, or our materials are currently being used. So the context, why lightweight bio-based composite? So obviously, almost 98% of composite reinforcement comes from glass fiber. And the slide on the below left-hand side, I have taken from Professor Ramakrishna's presentation. So as you can see, the use of materials is exponential. The materials available is very finite. So if we are continuing using in the rate with current technology, we need a lot of material. So almost we need 3 and more earth for us, but there is only one earth. But if we look to the different materials and their contribution towards CO2 emission, obviously, so 74% of CO2 greenhouse gas emission is a large contribution coming from materials. Then obviously different materials have different contribution. So if you have got methane, there you have got a maximum CO2 28. If you go to nitrous oxide and N2O, then you have got 265. So what kind of greenhouse gas you produce from your process and materials? So as you can see on the right-hand side, there are a lot of things happening. The flooding happening, the ice melting, drought, extreme weather condition, bushfire in Australia, in the USA. There's so many things happening because of industrial activities. Because of materials not being used very wisely, because of the materials that are not sustainable, not renewable materials that are currently being used in a very high percentage of 98%, as I saw that. So there is a tremendous opportunity for us to work sustainable materials. So just what are the opportunities coming? Wherever we see problem, there are the opportunities. So we can see these are the industry sector. I think we can use our materials, natural fiber composite, plant-based materials, or bio-based materials in biocomposites, for example. So space, aerospace, the marine, automotive, we have been working in this particular area. I will share some of the results with you later on. Renewable energy sector, for example, wind turbine, tidal blade, we can work. We are currently working a EPSRC proposal for that. Building and construction is another massive area that these materials can be used. Defense, maybe some, and textile are huge. So if we look the contribution coming from CO2 coming from these different sectors, you can see from construction, from textile, from packaging, automotive, marine. So there are so many areas that we can work the opportunity. Just want to go to the right-hand slide, packaging material. There are 2018, 46% of the packaging materials was from plastics, non-renewable plastics. So that area alone has massive potential for us to involve, along with other areas. So space, aerospace, marine, wind turbine, automotive, construction, building and construction, these are the key application areas where we have opportunity to use these materials. Now I would just like to say, okay, well, these are the key application areas. How do we fit our materials? Not everywhere you can use these materials, but the key thing is that what are the key performance targets for these various applications? This is very important for us to understand, and then we develop our materials accordingly. So for example, if we are going to space-related applications, then the challenge is the mechanical performance has to be very good. Obviously, tensile, flexural, impact, fatigue, vibration, damping, creep and fracture, toughness. These are very important properties that we need to have in our material if we are going to space. Then obviously thermal stability is very important. CTE and then TGTM. Gas barrier properties, long-term durabilities are very important. Lightweight is always there, important. Then flammability behavior, these are also very important. So, and then damage behavior of this material. So where are we using our materials? That is very important. And then we can tailor the properties, we can investigate performance accordingly. But it doesn't limit which area you can apply or which area you can't apply. So I want to go back again, space application of banana fiber. Maybe there is a way we can bring this material for that application. So if you want to go to automotive related application, obviously you have worked here. I was very impressed by your presentation. Lightweight composite materials in automotive application. Obviously mechanical performance, again, very important. And then thermal stability is very important. Lightweight is another key characteristic in the automotive sector, because the CO2 reduction in the automotive sector has been very challenging for OEMs. So they would like to use a lightweight material so that they can reduce CO2 emission by using less fuel, and then eventually you will have less the damage to environment. So so these are again key performance targets that if you are going to use this material in automotive sectors. But if we want to go to packaging application, again, these are certain, mechanical performance is important, obviously, but there are other key performance for packaging sector. So thermal stability is important, elastic modulus, loss modulus, that is coming from dynamic mechanical analyzer. Then barrier properties are very important. Oxygen barrier, moisture barrier, flammability is not so amazingly important, but still important. Antimicrobial properties are important. So what are the facilities you have in your lab? What are the facilities that collaborators have? And then what are the things that we want to develop? Because research is done in the collaboration. These days, research cannot be done in isolation. So some of the facilities that you have got amazing. Maybe some of the facilities we have got, you don't have got. That's what we share together. So these are the key performance targets for packaging application, for example. So what my point is that the materials that we are developing, bio-based composite materials, have got tremendous potential opportunities in different applications. The performance targets needs to be understood and then accordingly tailored. So again, the slide just understanding the properties, structure, behavior is very important. So obviously different properties are there, and that if you use different manufacturing process, you have to follow different parameters that will influence properties. And then when you develop this material, then obviously you do different advanced characterization techniques that will help us to understand material behavior, and then you can tailor that in design stage. So this performance structure property relationship is very important that we understand, so that we can tailor the application areas accordingly, or we test. So I don't have much time left. I want to go a bit faster from now on. So I just want to share two projects that we recently completed. One is called Flower Project. It's a European project that was 4 years long, and it was 4.6 million euro. And we had 8 different partners, 4 academic institutions and 4 industrial partners. Our aim was to develop lightweight composite material only from flax fiber. So, and then we were very concerned how we recycle this material after end of life. So different parts. So we had very key target, developing non-woven composite and non-cream fabric, triaxial, biaxial, and use this material for advanced application for boat building and automotive applications. And then within this project, I'm very proud to say that we had 4 PhDs completed. 4 years, 4 PhD completed, and they were amazing. I just want to share with you, maybe some young researchers here. They published more than 30 publications in very high impact factor journal during 4 years period. And one paper was published in Progress in Material Science, and I really commend that particular work. Obviously, different PhD scholars have published very good papers in different journals. They all deserve mention, but I just wanted to mention that we can make difference. If we believe and if we work during PhD, you can publish amazing papers, but you just need to believe and just do it. So these are some of the examples. We really looked on flax fiber. And this was done in University of Portsmouth using our X-ray microcity, looking at the flax fiber morphological structure. Where are the king bands? Where are the defects? And how that defect can affect overall performance in resultant composite. Yeah, so again, understanding fiber structure and morphology was really important. So some of the work that carried out during this project was very interesting. So yeah, due to time factor, I can't go too much detail. Then we understood those factors. Then we looked mechanical behaviors. One of them was vibration damping behavior. We compare with existing carbon fiber, and then we use flax fiber, which is hybridized with carbon fiber, using different stacking sequence and fiber architecture, and we were really able to bring very high damping properties of flax fiber compared to carbon fiber. Just one example, and this material was used in boat building. Yeah, so understanding the vibration damping behavior was quite important. Again, the application is what it determines what you need to investigate in this situation, for example. Then we do a lot of impact testing and then characterization of these materials. And then again, just I showed earlier how we got this amazing property. I'm very proud of this. And then this developed composite was used in a marine application. And this was just the process that was used within this project from one of the partners called Keros. And then we managed to bring this product finally. So from this project, this product was developed, and it is currently being used. And it is in France as Concarneau. And then you can go to Keros and see how this product is behaving. So replacing glass fiber with flax fiber in marine application was a big achievement. So yeah, so I'm very proud of it. So then we also work on automotive, so headliner. So again, replacing glass fiber from flax fiber. We managed to do this, and this is currently now being used. We were also able to win TEC award from our new material from this project. So what I'm trying to say is there is a possibility, there are a lot of opportunity for plant-based, bio-based composites to be used in a high-end application or advanced applications. Happy to the partners. There are another and then partners. That was in structure, look their performance, and then how different temperature and humidity affect overall performance. That was also very interesting result that we obtained from this project. Then obviously we work on other materials using fracture toughness behavior, impact toughness behavior to understand their performance and damage behavior so that these materials can be used for high-end applications. Again, the aim is to use semi-structural applications or even sometimes structural applications. Who knows? Right, so we also spend a lot of time on machining of this composite, understanding how this material behave under different machining conditions, especially drilling, and then how damage progresses. So that is also very much part of our research work at the Advanced Polymer and Composite Research Group. Right, so life cycle assessment, bio-based composite, they have outperformed conventional material, and this was the work that Professor Monti and his team have performed in University of Guelph. So I just captured that result just to encourage us that the life cycle performance of bio-based composites are far better than conventional material. So again, we have different techniques available for us. We just need to adapt them according to our requirement, according to application areas and according to performance target. Again, this one of my PhD students was working in this particular piece of work looking flux toughness behavior of flux fiber composite and then hybridized with basal fiber just to enhance performance. Well, in conclusion, we need sustainable materials, no doubt. So we can use bio-based composite for advanced application, definitely, provided we address the performance targets requirement, adjusting different parameters, and different approach can be used to enhance performance and achieve the performance targets. There are significant opportunities. Obviously, there are still challenges ahead because understanding damage behavior, failure behavior, and understanding the application of this material in certain applications is still not fully understood. So there are plenty of opportunity for us to work in this area. Thank you so much for your attention.
Thank you, Professor Dr. Hamnat Daikal, for a wonderful talk. Your idea regarding lightweight bio-based composites for advanced application are thought-provoking.
Thank you. Is there questions or we tackle question later on? I've gone a little bit further than I supposed to be, so excuse me for that. Any questions? Later on. Okay, thank you. Thank you so much.
Thank you very much, the first keynote speaker of the day, and also thank you, Dr. Dow. For the next one, I would like to invite Dr. Santich, research scientist of KMU TNB, to introduce about our second keynote speaker, please.
Thank you, Honey. Good morning, everyone. I will now invite and introduce about our second keynote speaker, Professor Dr. Sriram Ramakrishna from NUS Singapore. Professor Sriram Ramakrishna, Everest Chair, is a wonderful renowned scholar of crossfield at the National University of Singapore, which is ranked among the top 8 universities in the world. He is among the world's most influential scientific minds. Clarity Analytics recognized him among the top 1% highly cited researchers in the world. He is listed among the top 25 scientists in nanoscience and nanotechnology by Stanford University. He is recognized as the guru of electrospinning and nanofiber applications. His publications to date received an H index of 191 and 1,77,560 citations. Highest professional distinctions include an elected fellow, Academician of Chinese Academy of Engineering China, Royal Academy of Engineering UK, Indian National Academy of Engineering India, Asian Academy of Engineering and Technology, and Singapore Academy of Engineering. He is also an elected fellow of AAAS, ASM International, ASME, AIMBE USA, IMEC and IOM3 UK, ISTE India and IUBSE. He received his PhD from the University of Cambridge, UK, and the GMP training from Harvard University, USA. And his academic leadership includes NUS Research Strategy Vice President, Dean of Faculty of Engineering, Director of NUS Enterprise, Director of NUS Industry and Technology Relations Office, Director of NUS International Relations Office, Founding Director of NUS Bioengineering, Founding Co-Director of NUS Nanoscience and Nanotechnology Institute, and Founding Chairman of the Solar Energy Research Institute of Singapore. He is a leading voice in Singapore's circular economy and decarbonization advocacy. I now heartily welcome Professor Dr. Sriram Ramakrishna to deliver his keynote speech about sustainable materials, plastics, fibers. Over to you, Professor.
Good morning. Good morning. Very good. Yes. Let me congratulate the university for the 65th anniversary. Also the organizers for having this conference with a focus on eco-friendly fibers and polymers. I say congratulations for that title itself because through my talk, I fundamentally would like to emphasize the future growth for markets is sustainable fibers, sustainable polymers and materials. And I truly believe, and that's the reason I congratulate you for having this conference with that specific focus. And I also, like as Professor Homdakal has 60 slides, I already foresaw he's going to use 60. I decided I'll have 70. No, we are not competing. But the whole idea is to give you a comprehensive picture. I know you are thinking this guy is going to torture us for 70 minutes. No. I will definitely do within 20 minutes. Sanjay told me, Professor, strictly 20 minutes, otherwise no lunch for you. Right? So what I've done is, well, I'm quite a seasoned presenter, so okay, there's no, the pointer, I'm looking. No, it's okay. No worries, that's okay. I can. Yeah, yeah. Oh, that's in the center. Okay. Oh, okay. So this is nice. It's almost like a movie. You guys can see this LinkedIn. So if you can go to that LinkedIn page. I already placed a copy of my presentation. So you don't need to click or you don't need to worry. You can go there, just download it. It's available and it's very easy. So 70 slides, I'm not going to go through all the slides. I will focus on very few important slides and save the time for the future or other presenters, okay? So I think as everybody else normally introduce their own institution, and it is expected I do that. So I'm from the National University of Singapore, which is ranked among the top 8 universities in the world and #1 in Asia. You want to get a sense of what does it mean? There are about 20,000 universities in the world. And in Asia, we are about 10,000 universities. So that gives an idea how this internationally, globally, higher education look like. So our university actually publishes, our university professors, close to 14,000 papers per year. It's massive. So, it's a very strong research-intensive university in Asia. We have lots of 44 highly cited researchers. I've been in this list for the last 10 years, so I'm glad to report that. So now, in the context of this conference, which is about eco-friendly fibers and polymers, so this is a standard where I'm involved. It is a Singapore standard. We released recently about sustainable packaging guiding framework and practices. So essentially, the industry responds to the national standards and international standards. If you want to drive change, you need to set the new standards or adapt the standards to your own country so that the industry can play their role. It's very important when you are actually marketing a product. Standards, compliance, insurance, all those things play into the role. So this is a standard we released recently in Singapore. So that's an outline. Materials, polymers, fibers, circular economy, circularity, bioplastics, case studies, and conclusion. I would not go into the detail, but essentially our world, modern world, would not exist without plastics. There's no way we can imagine a world with no plastics. We have to live with the plastics. There are 400 million tons of plastics are produced every year. There's also concern, massive concern about the unintended ecological human health effects of polymers. So we are involved, I'm actually representing Singapore government in terms of intergovernmental negotiations on limiting the total production of plastics. So right now that discussions are going round 3, and the idea is come up with a list of additives that are there in polymers that would cause harmful effects on the human health and ecology. So there's a list, and then eventually all the governments have to agree. When that binding agreement comes into the picture, it's a massively impactful on most countries. And that's where the eco-friendly polymers and fibers play a very important role. And that's why I said I congratulate you guys for thinking ahead. And so I won't go to the details. Traditionally, life cycle assessment, we focus on carbon footprint, looking at some of the impact on the environment. But there's also increasing focus on ecological footprint, looking at renewability of the materials. So again, I take one step back why I'm very bullish in terms of the stock market language. I'm very bullish about this area because fundamentally I'm a material scientist and I look at the past and future, and I believe this is actually what's going to happen. So if you look at the bottom that chart, we say if you are a material scientist, we always say the world started with stones, and then we went on with lots of manufactured materials, synthetic materials. So the question now is, if you look at now and the future, I believe 2 important fundamental directions for the materials world. One is intelligent materials, other one is sustainable or low carbon materials. So I won't go into the details in terms of intelligent materials, I just want to give an illustration. Normally we associate intelligence with the humans and living beings, but that's no longer true. So we don't associate intelligence with the materials. So the future is to make the materials intelligent. And there are early signs of how to design and engineer materials at different length scales and make them intelligent. So, but today's lecture is not on intelligent materials, it's about sustainable materials. So I will focus on the bottom one, that is low carbon materials or sustainable materials. So that's my definition. Sustainable materials or low carbon materials or eco-friendly materials are the materials that foster a healthy living ecology and a circular economy where the elimination or reduction of associated greenhouse gas emissions, wastage and resource depletion. They are purposefully designed or selected with a lower ecological footprint, social cost, higher circularity, while satisfying the cost as well as functional requirements. In other words, they are less detrimental to the Earth's ecosystem and human health. You are wondering, why is this guy reading it out? Because I'm conscious there are many other listeners online. It's a very important message, and that's the reason I read it out. So we are actually framing the research in a way. There are many researchers with different backgrounds. How can they come together and achieve futuristic materials? That's why we need a framework, we need a definition, a good description. Without that, it's like you don't have a clarity which way to go. Okay, that's the details. Now I would jump quickly. This is a linear economy which we talk about, a circular economy, Singapore Green Plan, which is where I'm also deeply involved. Singapore is going very strongly towards what we call towards zero waste country. So again, it's a very wonderful thing to look at. Okay, so now we get into the plastic circular economy. There are different approaches. Primary underpinning concept is recycling or upcycling, but that's not the only part. But right now most people are familiar with that one. Within that you have physical, mechanical recycling and chemical recycling. And you already see some of the examples in terms of the textiles. So these are the details when you look at plastic waste management, what really happens. And these are more details. this is what I think. In the future, we have to see beyond mechanical and chemical recycling. We would have to look at biological processes for recycling. So if you're looking for more high impact, better in terms of sustainability, circularity, you would have to look at biological recycling systems, which need to be developed, which need to be scaled up. Again, it's an opportunity for new countries, new players to innovate. Okay. So now material circular economy. The paper is already published, so you can download later on from the journal website. So we carefully articulated what are the principles for material circular economy. So these are 10 principles we came up. Again, as I said, when you are guiding research directions, you need to articulate the framework and principles. These are our principles, which is quite widely accepted. So those are the details. So my student, he's a former Thai student. He's now has a company in Thailand. He has done this analysis, and for example, end-of-life waste management of plastics and composites. If you do the life cycle assessment, based on the boundary conditions, how you actually analyze it, you get different answers. So don't ever believe whatever is published in some journal paper. That's actually for their context. In your country, in your community, you have to assess again, because your boundary conditions are different, you're going to get a different answers. So even though it is a paper published by the most famous or most influential scientists, I'm not saying they're wrong. The question is they assume different boundary conditions. You really have to assume your own conditions, validate them, and come up with your assessment, and then go for it. Otherwise, you will be accused of greenwashing, for sure. Okay, so those are details. Then this is ISO standard I'm also involved. We just released it, ISO standard for circular economy. Now it's been already released by the ISO. And these are the details. When you have a new standard, normally it comes with a series of standards. It's a framework, definitions, how actually to conduct that particular methodology. So these are the things. And this is a book we have written on this one. If you are interested, you can actually get a copy of the book. It looks at the new concept about circularity. And then there are the details. So we can look at all these different aspects. This is very systematic aspects and case studies, and then essentially it's about metrics, framework, methodology, boundary conditions, and actually making an interpretation of the assessments. That's basically it. So it's not only us, I think the general public, media also believe circularity is extremely important when we are talking about plastics, and especially when you want to go towards sustainability, eco-friendly. You need to understand the concept of circularity much more broadly. Okay, so now I come to the concept of bioplastics, eco-friendly fibers. Again, we release another standard in Singapore, technology review. It's technical reference, sustainable packaging guiding framework, where we define what is bio-based, what is bioplastic, what is biodegradable. Because as a researcher, you understand, but industry do not understand, and the markets do not understand. So you need to help them. Otherwise, you are all speaking different language, and that doesn't really help. So you really need a standard which basically guides the industry. So we have come up with this guidance. So this is called Technical Committee on Circularity of Materials. I'm sure Thailand may have one like that, or they should have one like that, because that's important, because otherwise there's no guidance to the industry. So, as I said, my former PhD student, Pia, that sounds like a Thai name, right? Yes or no? Good, because I know you're all sleeping already. I need to wake you up. That's the reason. So you can see that guy, he actually worked for the project of the Asian Development Bank, and his focus is on bioplastics. So they did a very extensive study about the bioplastics in the context of Thailand and the world. And I really recommend take a look at this report. It is very detailed. It's there. You can download it. So the point here is we look at all of them, and the policies of the countries on bioplastics is not uniform. You all like to believe, everybody like to be following the same view on bioplastics. Answer is no. You could see South Korea, Netherlands, Japan, Italy, US, and France. They have a different opinion. And so is Thailand, so is your neighbors, Philippines, Malaysia, Indonesia, Cambodia, I'm sure Singapore. So it's very important for you to, again, understand what is the policy imperative for your push on bioplastics. Especially when you manufacture something, you want to sell abroad, this comes into the picture. So that's the reason we need to know exactly, precisely, what is the national guidance and policy on bioplastics. So I won't go into the detail, you can look at it. But I really think it's a good strategy for Thailand, of course the world, bioplastics, because sustainability is very important, and bioplastics in my sense has a role, and I believe it's very important. Okay, so these are how we actually can define bioplastics. They could be bio-based, biodegradable, non-biodegradable, then polymer-based. And then again, you need to segregate them in terms of combinations. So it's papers already published, you can look at those references. So this is how you make bioplastic, an idea. Also, you can make bioplastics from the waste. That's the reason I'm quite bullish about bioplastics, because there's lots of agricultural waste and food waste, and they need to be valorized. Otherwise, there's a lot of mountains of waste being built up. And providing a higher value proposition is the right way to move forward. And these are some ideas like cellulose waste or polysaccharides, and some of them. And then these are some already in the market. Some of the agricultural waste, food waste based bioplastics. Some companies are already selling in the market, so it's a good reality. So these are volumes. We think that would increase with time, and specific materials, in case you are interested in a specific polymers, which one to focus on. And these are more details. I won't go into this one. Okay. These are life cycle assessment analysis. Okay. So now I come to the case studies, mostly about my own work in fibers and polymers. And so now is actually a self-story. So my journey started with composites 85 to 95. I was focusing on fiber reinforced composites, and we looked at lots of those interesting properties. But then 95 to 2015, I focused mainly nanofibers, or air filtration, water treatment, regenerative medicine, wound dressing, composites, energy generation, energy storage, sensors, and personal protective equipment. And then more recently, we are now focusing on wearables, smart intelligent fibers, sustainable fibers, fertilizers, food packaging, and synthetic meat or artificial meat. So in other words, when you are doing research, if you're broadly collaborative, it opens up horizons, and you could do a lot more than what you think or what you set out to do. That's very exciting, because you learn from so many different disciplines and so many other collaborative researchers. Okay, so as I said, that was how my journey started with automobiles and fighter planes. That's how the fiber reinforced composites we started in almost 34 years ago. And then worked also a little bit on using, say, waste, for example, coffee waste, how do you make it as a flame retardant materials. And we have a project in Australia, which is about well-funded, about sustainable fibers and composites. It's a $5 million Australian project. And we are also working green composites in China, and the details, I think, at a later platform we work on, we can let you know. But we're looking at bio-based sourced fibers as well as resins. So this is a large program that's happening. Okay, those are all kinds of different fiber materials. In Taiwan, I have a collaboration where we look at specialist natural materials for undergarments. So those are examples. In India, I'm now just started a project called Etriwear. I do not know. Those come from Tamil Nadu would know. It's a very fast-growing grass. And then we are looking at, apparently I didn't know this, from that Etriwear grass they made sari, silk sari, not Etriwear fiber sari, and that was actually given to the Princess of Thailand. So I cannot read Tamil, but if anybody can read Tamil, you can check it. And so they told me that a few years ago, they actually made woven a sari out of that and given to the Princess of Thailand. So that's a good story. Of course, you can also use that for building materials and construction. Okay, so these are the story of why bioplastics in terms of circularity, sustainability, some of the assessments we have done. I also work with another company in Singapore where we are looking at food packaging. So these are basically bioplastics, biopolymers. With KFC, for example, if you go there, you would have this biopolymer-based trays and cutlery. When you dispose, along with the uneaten food, the whole thing can go into the digester like that, and then it is a special built digester, and that would do the valorization. So if you're interested, this company is in Singapore. And I just have to congratulate Thailand because I was visiting Envico, one of the large company in Thailand, recycling, amazing. So they have 30,000 tons per year plastic recycling facility in Thailand, amazing. So if you have not visited, I promote this company. It's good, very good, massive company. And so I visited them last year and it's good. And so then we also look at recycling materials for apparels. The Asian Polymer Association, which some of you are familiar, Reliance is making a big push for PBAT as well as the polyolefins, what they call circular polyolefins. So they're actually scaling up into a large production capacity. So again, one could check that one. And then most of the recycling is normally for the rigid plastics, but flexible plastics, flexible polymers is not easy. It's a big challenge. So now we have a different strategy for that one. And then my own work in the last few years, electrospinning, just I'll give you the introduction. It's a very popular technology of making fibers. And so this is the way we apply high voltage, low electricity, and then we can spin almost hundreds of different polymers into fibers. And so those are the techniques we developed. And we integrate them into the textiles. So we're not talking about just lab-based. We actually scale it up to the industrial scale. And so that's how we work on the structure, morphology, performance, behavior, and then lots of other things we do. This is the future, how it look like. And the conclusion, basically, I fundamentally subscribe to sustainable materials. You want to call them eco-friendly materials. That means subset is eco-friendly polymers and fibers. That's the future. And that is a future we must drive. And those are the numbers on the Forbes. Bioplastics is about close to $45 billion in the next few years. And textile industry is also going through massive transformation. Sustainable textiles would be about $150 billion. So I'm quite actively involved in helping out some of these directions. So recently there's a paper published in Nature Materials, not our paper. They say that advanced materials provide solutions toward a sustainable world. So this involves designing materials, making materials differently, and envisaging products in a different way, and then reaching the markets and changing the world. So with that, I'd like to thank you for the opportunity, and I hope it was helpful to you. Thank you. So, well, he said no questions, so right? Actually, he didn't say it. I'm saying myself. What if...
Thank you, Professor, for your keynote address. We have a short question. Is like if you.
Okay, so I think they decided I can't give this guy even a dinner. He doesn't ask some question.
Like if anybody is having any questions. Or
In a business world, we call that ROI, return on investment. So, any questions? You can ask any question. Yeah. I have wide experience. Anything, yes. I thought except you. Okay. Yeah, that's okay. Very good question. Thank you, first of all, for your compliments. Early morning, somebody says you are great, you feel good, right? Even if you don't, even if I'm not great, that feels good. Thank you. So I don't need extra coffee to feel better. Thank you. But a serious note, while we say sustainable materials, products is the future, there's a lot of challenges. But these challenges are going to be surmountable for different reasons. But why it is challenging is there are structural reasons. Because any product, any manufacturing is globally integrated. So, and geopolitics are complex. Financing is complex. So the investments. And then in the real business world, the different suppliers undercut each other. For example, somebody is pushing, say, let's say your flax fiber. For you to reduce the cost, you need to increase the volume. But that requires somebody believing and investing. But there's someone else who's already trying to stall it. So this kind of competition is happening. But why am I still bullish about it is because 50 years ago, the world, there's only a few places there is a manufacturing high quality, and there's lots of high-level thinking in only a few geographies. We're talking about 2024, the world is much more level playing field with all its problems. There's lots of knowledge, lots of skills, lots of resources and money now globally spread. People understood that they need to play the game, and I strongly believe the entrepreneurs in these parts, other parts of the world, they are finding their way to scale up and prevail in the market. So as they gain experience, it's a matter of time, they will change, and that will happen. And then on top of that, the global policies, which is pushed by United Nations, is firmly in this direction. That is, towards decarbonizing the world. That's the direction. So I don't think United Nations will take a U-turn on decarbonization. So United Nations mean all those 200 countries. They all sit around in different places and they keep pushing decarbonization. So when they push for decarbonization, obviously there is a role for this one. Why am I more even bullish is, if you do not push this direction, it's impossible for you to change the industrial architecture of the world. By pushing this one, you can allow new players to come. Because last night in a conversation, I understood Thailand, for example, has lots of bio-based materials, agriculture and other means. So you have a resource with you, and you need an opportunity. So if the world is not pushed in that direction, there's no chance, because they can always price you down. So with this new push globally, and there's also more ubiquitous awareness, knowledge, skill sets, financing available, I do think that's the way it's going to go. Sure. Thank you. Yeah. So for that, I need you to go back to the history. So I used to attend the Farnborough air shows in London, and in late 80s or mid 80s, fiber reinforced composites was not considered as a solution. They were all thinking about aluminum only for the space, the aeroplanes. Right now, if you look at it, 2024, most of the aeroplanes, especially the military ones for sure, 70% is actually fiber reinforced composites. And that's because carbon fiber, they have a series of carbon fiber developments. The latest ones are phenomenal, the amount of elastic modulus and strength they can achieve. And then also they dealt the problems associated with the interface between fiber and the matrix. There are always problems. That's the source of weakness. And nice coupling agents have been developed, and people have ensured there is a durability. So now the question is, natural fiber composites right now, as well as in the past, have always been subjected to few issues. One is the variability of the material. The feedstock is a natural material, so you can't ensure the consistency or the molecular level consistency. Second one is properties are widely distributed. So this is the challenge generally posed. But I think these can be solved, and definitely they will be solved. It's a question of thinking a lot more scientifically and apply new technologies and deal with them. For example, we all know a bulk material will have more defects. But if I reduce the dimension to micron and submicron, I control the defects. So now there's a lot of new technologies available in reducing the dimensions to a much finer, and that's where you're going to get the second one is there are other additional processes you can introduce, for example, ionic liquid concepts. So that's an opportunity to integrate new knowledge, new thinking, and deal with those specific problems. Now the question is, aerospace, deep space, do you see an opportunity? Space is not uniform. Even the drones, for example, you can say it's space. There are satellites just, right now our planes fly about, let's say, 10 kilometers, 11 kilometers from the sea level. But if you go 12 kilometers, already you are in the space, right? So that is not as aggressive as a deep space. So the radiation, cosmic energy, and then also the life. You don't need to design a satellite that will last for 100 years. You probably design a satellite that will last for a few years. So the fit for purpose is different. So one should not necessarily think there's a very rigid definition of space applications. So there would be opportunities for differently performing differently designed systems, and some are designed to disappear. Right? So space debris is a serious problem. That's one issue. And the other one is the way of mitigating space, what do you call highly demanding functional requirements could be looked at with designs. So I'm optimistic. If you want me to tell which specific ones, we probably can go through component by component, and then we say, hey, this can be done with a bit of tweaking. I would say one can be optimistic. Yes. Same way as you go into space, you also need to go for the deep sea. Deep sea is always forgotten. The human world is going to go deep into the water as well, and deep into the earth crust. So you can imagine possibilities in different ways. Not only that, Professor Homdakal knows, I advise a university in Nepal. When we brainstorm in Nepal, which is a mountainous country, they could use a lot of bio-based systems for their mountain engineering as well as the living conditions. And the functional requirements are different, but also the longevity is different. So I actually see functionally demanding applications even on the terrain, because terrains are not the same. And second one is climate change. Right now, if you look around, the bus shelters, wherever they had the fiber reinforced plastic, they all change discolor. After a few years, rooftops discolor. So we need to innovate. and I'm sure we don't need to worry too much about space only. There's a lot of things on the systems, and even the water salinity is changing quite a lot. So imagine you have pipes which are made of your fiber reinforced composites. The salinity of water is changed. Similarly, we're going to change now systems for transferring energy. Right now, oil is sent everywhere, but they're going to replace it with LNG. After that, they're going to replace with hydrogen very soon. So the question is, how do you transfer hydrogen? Yeah, and definitely you need a lightweight system. So why not? So you don't need to be deterred by only deep space issues. There are a lot of opportunities on the ground because things are changing. And I believe and I put bets on hydrogen economy for sure. The reason is, I know EV is important, but EV comes with benefits, but it also comes with lots of environmental issues. So I tend to believe that fuel cells and hydrogen-based concepts. So again, the fuel cell systems require lots of your sustainable polymers, membranes, and designing things differently, and they're going to go into the transport systems. They need to be designed for a higher safety as again issue, the fire issue, impact issue, all that stuff. So actually you can be busy for the next 100 years with all kinds of research. So if you are worried, oh, you know, my ideas are all gone and I don't have anything else to do, don't worry, there's plenty of work to do. Absolutely. You will never be out of the business. I'm very sure about it. If you like, we can place bets, yeah? Sorry, yes.
Thank you, bro, sir. He's having any question?
Yeah.
Okay.
Otherwise, he will not let me go out.
Okay, bro.
Yes,
Okay,
yes.
I think last question you can
He said last question. If you have any other questions, ask together. Well, I will say together is last question. Okay. Sure. Yeah. So in case you didn't hear, unable to hear the question on the back, because you didn't have the mic, so I'm just repeating. There is an opportunity for submicron or nanofibers and bio-based nanofibers. My suggestion is you have to look at from the application point of view. Certain applications are actually not a large volume. So we like to believe composites is a large volume. It's actually not a large volume. Whereas the textiles, plastics is a large volume. So based on the first thing is the global, of course, how ambitious you are. If you want to change the world, you have to be ambitious. So if you're ambitious, you have to get the boundary condition right, which is basically what is the global volume. So my sense is you are looking for composites, it's not a large volume. While we like to believe it's a large volume, but it's not. So then certain technologies it's fine. For example, nanofibers, electrospinning, it's okay. And there are other technologies. But if you're looking at really large scale application, there are melt-blown technologies, and there are other further improved island technologies are available where you can make these fibers. And the second one is the scaling up. You could also innovate a lot now. And so bio-based polymers, making them into nanofibers require a lot of optimization, and more research need to be done. The next one is how do you integrate nanofibers with other substrates? That's one issue. So if you're talking about, say, let's say filtration, you do need a nano layer, microfiltration. But what happens is when it is fouled after one use, you need to do the back flushing. So that requires you to have a better mechanical properties and adhesion. So when you're looking at biotechnology, water treatments, we normally look in that way. So there's a good opportunity. Then the other one is you could play with chemistry, and then you could what they call single pot technique, and then you can improve multiple functionalities into one. I think there are a few ideas. So if your concern is there technologies that can be of large volume scale-up basis, there are. Again, if it is a textile kind of application, that's even massive. Now, I don't want to use tobacco smoke industry. It's massive, but some countries they don't like us to talk about it because it's banned or at least discouraged. That's again large volume. They need these fiber technologies. Yeah. So I'm optimistic, yes. So this is the last question minus one.
Okay, Professor, I think we can take this as the last question.
Okay, so right now there is no bioresin that is of such scale available, and is also expensive. Some European countries like I think France or Italy, some other companies, France, yeah, and they already saying they have it, and but it's proprietary. And again, I'm always an optimistic guy. When you go back and look at DuPont 50 years ago or 100 years ago, they're nothing, right? So they came up with all kinds of polymers and understood at the molecular level and figured out how to solve the problems. So I'm very optimistic it can be done. Sure. Yeah. Okay, first thing is the intelligence is defined as you sense the surroundings, you make a decision, and you make the decision for the best interest of yourself. That's basically intelligence. Yeah. So human intelligence we understand. Basically, human intelligence is nothing but a memory and processing. You all may like to think you are something different, but that's all it is. So memory, because you have a lot of experience. No experience, no memory. The first thing is listen to everything. That means you're forming the memory. Then you process it and becomes intelligent, right? This is basically how we define what is intelligence. Now, in the context of materials, we need to design materials such that there is a sensing function. There is somehow, it makes a decision to have an optimal response. So that's the concept. Now, if you say what kind of systems I should go towards, I would say wearables. Wearables is an area going to massively improve worldwide. I think that is one. And the other one is transportation system where there is a higher demand for these systems. For example, aeroplanes, the surface, they want to have a better feedback system, information about it. So some of these high-performing, you could consider intelligent systems. The other one, of course, is say normally biomedical applications, but that's very challenging because anything that is interfacing blood and tissues comes with the highest regularity. I need lots of money to pass through all the regulatory requirements. It's okay to publish a paper, but you really want to see that as a product sold in the market. You need a lot more resources, a lot more efforts. If you're talking about human tissue or blood contacting materials, for sure. Yes. If I don't stop now, he's going to move me at the dais. So, sure.
Thank you, Professor. Thank you for your keynote address and a wonderful discussion. Thank you, Professor. I now invite Dr. Kret, Assistant Professor in the Faculty of Technical Education and the member of our NCR group to introduce about our third keynote speaker.
Okay, thank you, Dr. Satish. Good morning. Professor Mohammad Javed is our next keynote speaker. Dr. Mohammad Javed is currently working as Distinguished Professor at the Chemical and Petroleum Engineering Department, United Arab Emirates University, UAE. Earlier, he worked as Senior Fellow at the Biocomposite Technology Laboratory Institute of Tropical Forestry Product, University Putra, Malaysia. And also has been working as visitor professor at the Department of Chemical Engineering College of Engineering, King Saud University, Riyadh, Saudi Arabia since June 2013. He also worked as distinguished research professor at Malaysia Japan International Institute of Technology University, Technology Malaysia, Kuala Lumpur, Malaysia. He has more than 24 years of experience in teaching, research, and industries. His area of research interests include hybrid composite, lignocellulosics, reinforced filler polymer composite, as one material of graphene nanoclay fire retardant modification and treatment of lignocellulosic fibers, and solid wood biopolymer and biopolymer for packaging application, nanocomposite and nanocellulose fibers, and polymer blend. So far, he has published 70 books, 90 books chapter, more than 500 peer-reviewed international journal papers, and several published review paper under top 25 hot article in Science Dialects during 2013-2020. He also obtained 6 patents and 6 copyright industrial design, H-index and citation in Scopus R85 and 32,343, and in Google Scholar H-index and citation are 102, and 43,866 H-index in Web of Science is 75. He is founding series editor of 3 Springer book series. He worked as guest editor of special issues of several peer-reviewed journals. He is also professional membership of IOM, ACS, SP, APA, MySet. Besides that, he is also reviewer of several high-impact international peer-reviewed journals of SY, Springer, Wiley, Sage, ACS, ISC, Frontiers, 40 PhD and 17 master student graduate under his supervision in 2014 to 2023 in the field of hybrid composite, green composite, nano composite, natural fiber reinforced composite, nanocellulose. He secured various research grants at university, national and international levels on polymer composite of around 6 million Malaysian ringgit. He also delivered plenary and invite talk in international conference related to composite India, Turkey, Malaysia, Thailand, the United Kingdom, France, Saudi Arabia, Egypt, and China. Besides that, he is also a member of technical committee of several national and international conferences on composite and material science. Professor Mohammad Javed also received several awards at the national and international levels. He is also winner of Newton Uncle Omar Coordination Funds UK Malaysia Research and Innovation Bridge Competition 2015. I now wholeheartedly welcome Professor Mohammad Javed to deliver his keynote speech on eco-friendly food packaging tray from agriculture biomass.
Okay, thank you for giving a very long introduction. So first of all, I also congratulate to the King Mongot University for celebrating the 65th anniversary, and also the conference organizing committee, and who is taking the challenge of the eco-friendly, the materials which most of us that who is sitting here looking for the future, as the Prof. Shiram have already said, must be optimistic, and we all are sitting here on the basis of optimistic that, and we are promoting this material because we are optimistic that about the sustainable materials have a future there. So I'm just taking that one of the what we call that's the already the basic informations and all these things. The Prof. Home and Prof. Shiram already have given a lot of informations to you about the nature fibers and bio-based materials and all these things. So basically in this project I'm going to more talk about the specific topic only on the packaging here. So basically my presentation is on the eco-friendly food packaging tray from the agriculture biomass. And just for your information, I have just recently joined this university. It's almost just 1 month. So this is one of my first presentation who is representing the United Arab Emirates University. So this is the first keynote to speak on behalf of that new university. So I'm basically going to talk about the what you call that the sum of the things. Basically, why? Because we have already the materials available in the market on the plastics and all these things. So why basically we need the biodegradable packaging materials and how that can be done, and different types of the standard is available for the compostable and biodegradable packaging in different countries. And also that we have, on the basis of our research, we also done a startup company, Fiber Strong private limited company, and how we do the pitching, you know, because we are the academicians and we go to ask the funding and all these things. So that's also a very tedious job to do that one. And there is some things we done that one. So basically everybody know that the packaging is one of the importance, the things, you know, in our daily life. When we go to buy anything, we in the shopping mall or even food and other things, we need the packaging, you know. We cannot hold that things in the hand. So we need something which we can carry that material. So when we look into the statistical, that one, around 37% of the packaging products are made from the rigid and flexible packaging plastics, and most used plastic, the makes plastic the most used packaging material. And you look into that one, is one of the material that is using in the unsustainable manner, you know, that the materials is that. And there is different already, the earlier speaker already talked about the greenhouse gases and all these things, how it can, you know, that one going on. So if we take into that one, there are a lot of waste we are creating every time, you know. So we look that one, the statistical say that 2 garbage truck per minute, you know, in 2030, and then the 4 per minute is going to be in the 2050, you know, if we don't control the wastage, what we are doing that one. And this is the 31%. These are the some statistical. So we need to be clear that the food and beverage packaging are important contributor to the pollutions of the environmental. And agro waste, if somebody did not understand that what is agro waste, you know, so there simply you have to understand the residue coming and growing and processing of the raw agriculture product such as fruit, vegetables and crops is coming, that we generally consider as agriculture waste or agro waste, or what you can say that one. And they are the non-product output of the production and processing of agriculture. They may contain material that benefit man, but whose economic values are less, you know, and there the cost of transportation is high. So if you want to buy some that materials, it's cheap, but the transportation cost is going to be increased, that one, and processing for beneficial uses. So agriculture can be, the waste can become from animal waste, food processing, oil palm waste, and there is crop waste. There are different sources of that one. It can be from the wheat, straw, rice, sugarcane, bagasse, which is available in most of the countries in the Southeast Asian nations, you know. So basically the one thing why we need the biodegradable packaging, because the market of this product at this moment is large and growing, because everybody is looking towards the sustainable materials, biodegradable materials and all these things. So we have to go on that direction, because the market demand is there. And the growth is triggered to large extent by the consumer around the world, who are becoming increasingly aware of the negative environmental impact, you know. So like for example, people are looking how the marine animal are affecting from this one and all these things. So it trigger you, you know, how you can be avoid that type of plastics and all these materials. So this environmental regulation, some of the countries, like for example recently the India have implemented, a lot of European countries have already implemented ban on using the single-use plastic, or there is some limitation how much amount you can be used for that one. So there is also, this is a multi-billion business opportunity for the peoples, you know, to look into that direction, how you can grab these opportunities. These are the some of the effect you can get into the marine animal. If you put into the plastic into the oceans or sea, you can get the negative effect. These are the certain seabirds, cows, and all these things are affecting what you are playing with the plastics, you know, throw into that one. And basically I'm going to cover on the one of the project we done with the UK. It's around 3 years project. We just finished before the COVID this project. So that project we call Safe Biodegradable Packaging, and this is the involvement of the academic and industry, both involved, and this project target to commercialize the output, you know. So and that we targeted the raw material, because I work in the Malaysia, so we targeted that time the oil palm empty fruit bunch fibers, because the Malaysia around 45 million tons of the wild palm, the waste is available. So how it can be utilized? So you look this type of the huge amount of the empty fruit bunch available, after the palm industry have extracted the oil, after that they throw. So this is the huge amount. Is it this problem or not, So we have a very simple concept, that one. This one, you look that one, this is the plant and this is the fruit, and the fruit you can have clean up and all these things, and then you extract the fiber from that. And these fibers can be converted into the pulp, and then the pulp can be converted into any form of the pulp molding product without using any resins and all these things. So this is the concept. We come into the one direction. As you know that the palm oil is available cheaply and all these things are there. I'm not going more details on this one. So it's already established. People are using this palm oil from long time. And there are different techniques that you can change into that one. There is a wet type of that one, the pulp molding, and there is a dry types of pulp molding. So on the base of that one. So this is the one industry is a partner of our, that the eco premium packaging. So we done the trial. We make the 30 kg pulp in our labs, and we take this pulp there, and this is the pulverizer tank in that company. So you can put into the pulp here, and at that stage you can also mix up. Like you want to make a water resistant, you want to colors and all these things, what you want to do, you can add the pulverized tanks, you can mix with that one, and you can modify your product here. And this is that one. You saw that we are putting into the high speed agitations and low speed agitations. And this is the pulp slurry was pumped into the holding and mixing tanks. And this is the pulp molding, So this is the what call that the shape can be, this is because from the lunch box, but you can change into the bowl, you can change into the plate as per the mold design. So you just need the very good mold makers who can make the good mold for you as per your requirement, what are the product demanded. And that is the panel, This is the panel which can control the temperature, pressures and everything is there. And this is auto control panel. So this is the food containers going inside, and this is the first product we make from that one, because this is the tough product, and we look into that one, and we find out that this is a positive finding, that we have all the bondings and everything is very good from that one. So it encourages us from these materials. And the second trial again we done with the plates, we done that one, and we also find that. And parallelly, because this project is parallel from the Malaysia and UK. So UK also parallelly do the research, on the same things on that one. So they also started to make a what called the molding product by using a palm oil fibers, And they have some issues. Initially they have some issues. You look that they are unable to form, the properly. And then we visited to the UK and we look the problems there. What is the problem? And we find out that they have the problem in their mold, So we designed the mold in the Malaysia, and we taken this mold with the mold maker to the UK, and we fixed there, the mold there. And after that, you saw how beautiful product they are getting. This is from UK, So they from the same, they're able to make that one. And this is a small video. I don't know it can play. This is a small video if you want to understand. It's a 2-minute video. So what's the pulp molding? This is the final stage. She is collecting the product, and manually she is checking that one, the quality of the product. So this is the line of the pulp molding, what you call that, in the one of the factory they have 5 or 6, the line they have. I don't know, the voice is not coming, but only they have the voice. So this is the thing that what you saw, that the pulp slurry, the pulp is coming here. And from the waters, this step you look into that one. Just a moment. Here the pulp slurry that is going to come here, and after that, as your mold, they are going to hold it. So one time they hold it, and the second time they are going to press like iron, and then it will push out to that one, and then you will collect that. Plates or ball or what type of design you have that one, you can do it auto control. All these things are auto control. Just you done that thing and everything is controlled. You look that this is the coming from the slurry, this is the, you look this one coming, this is the your pulp, with the waters. So this is the one of the, you can later on, means you can explore that. This is available in YouTube's and other places you can get it. So we also done the, because everybody talking about the life cycle assessment, So we also in this project done the life cycle assessment. We taken the all data of pulp moldings and all these things, and we analysis the mass and energy what's the consuming by that industry and all these things. And we also try to look into that one, how we are going to put into the different product in our packaging, and we look the performance compared to the what the existing materials are there. So we taken the lychee, apples, tomato, and we look the in original and pulp molded product, how much the weight is going on that happened to that one. And we also look with the meats, and one of the target of this project is also to increase the shelf life. Shelf life means, if you don't understand the shelf life means the timing of the preservations, Like for example, tomato in the hypermarket, if 3 days, if you can increase into the 5 days, the hypermarket is very profitable, because in the 2 days they can lose it, and millions money they lost due to the timing of that one, that shelf life. Similar in case of the meat packaging and all these things. So we try with that one, we try in this different, and we feel the problem, so we put the patches and we look into that one. And we also took for several days, look that when it is smell, it is started to coming from this one compared to the plastics. So these are the some of the packaging. We find that no packaging failure was identified over the testing periods. And we also compare by the survey in the Tesco UK. We put our tray and we put the plastic tray, what is available in the Tesco, and we look the normal customer coming to that Tesco, and we ask them some question. And after that, this is the some of the packaging we done that one. And this is the another packaging we done with the Tesco current plastic punnet, and then we have the own punnets we use for mushroom, because mushroom is one of the very demanding and what called the fragile materials in the UK, it's very costly materials. This is our final product, we make it that once, and we also do the sealing. And the good thing with this packaging with that, then the plastic materials, we use that one. This is also a cellulose film, so it's a biodegradable, and the printing used here is also bioprinting. So everything is a environmental friendly concept here used in this packaging. These are the another some photograph for that our product. And we take the consumer survey, and we find out that the 85% of consumer found that the safe biopack packaging acceptable as the produced packaging. 8% found it neither acceptable or unacceptable, and 7% only people find out it's unacceptable, that one. And we also that the 42% of customer found the plastic packaging acceptable as a produce, So this is the survey we done in Tesco headquarter in the London. And we get this one, a respondent in around 180 people are there. So of course it's not taking a big groups, but we get some idea, what the people perception is about that one. This is another we done for one Malaysian company. They want us to make the what you call the sample for them, so we specially designed for this one. And beside that, we also done the how to use the palm fiber in the what you call the extruder and others. So we have a parallel by using with the biopolymer. Also we done the thermoforming and compression moldings by using this one. So this is the one of the partner company in Malaysia. We try to first formulate, because I am not putting here everything, First we have a formulation, we done the optimization of the formulation, and when we get the final formulation of that one, the polymers and fibers and all these things, then we make the sheet of that one, the composite sheet. And this composite sheet can be cut into the different size and different products. So after using this sheet, we fold it roll, some amount we send to the UK also, and we develop different what call that the tray by using a different technique. So we use vacuum forming machines, we use the multi-vac machines, and we also done the vacuum form composite packaging, and also we done the in the hot press, we just a normal hot press, we done that one, and we make different types of the tray. You look at the how beautiful that the very clear, everything look, and no coloring, but the color is come from the palm fibers, And we also use the others in that one. Backside you look very clear, and we have also the try with others, like this is the what you call that the pure PBS fibers, and then we also try with another fibers. We also try with the kenaf fibers, and others in bamboo also try. Lot of others we try with that ones, with the beside that project. And as we earlier already discussed about the other keynote speaker, that the Prof. Shriram, that there are different standards, in different countries there are different standards. But if you go into the UK and Europe, the EN 13432 is well accepted in the market, that one. And this is the bio-based materials in EU directive under the manufacturing composite, and they call that term as bio-based. If you look into that, what is the content? So these are the things they needed within that. The packaging material and its relevant organic component are naturally biodegradable. You cannot degrade by using any chemicals and all these things. And disintegrations of the packaging material take place in composting process. Like for example, you just put in the home soil of yours, and it can degrade, and it do not give any negative impact, and the packaging material does not negatively influence the quality of the compost and all these things. So if you fulfill all these things, then you can get. So there are different types of the company available where you can send the samples and they can do the evaluation for you, and after that, if you fulfill that one, then you can get this what called the standard from that one. And if you get this standard, very easy for you to sell the product in European market. Without that, even you say sustainable, compostable, anything, but you cannot sell that product in the market. So you need to get this accreditations from them. Beside this, there are different another standard available in the market. ASTM D6866 is available in the market, that is accredited by USDA, and they have different logo for that one, according to the how much percentage they degrade. And if you go into the Italy, there is a Vincote standards and issuing in the certificate in the Europe, so they have also the different, if how many percent of the bio-based materials you have, accordingly it can be give the different logo there, And there is another is in Germany, Dean Sato mentioned that bio-based content in the logo. So similar here, you can look into that one. If the 20 to 50%, 50 to 85%, and then you have more than 85%. So accordingly, you can get the logo on the basis of your material. And this is the list of the different countries, the following, like Malaysia, they have not directly standard, but they call eco-labeling, eco-labeling. Similar with Singapore, then the Thailand green level, these are the some, but this data is not updated to 2024, it's updated before the lockdown. So it's maybe certain changes come, but I hope that most of them are still available, this one. So this is the another standard in Japan, Korea, Vietnam. So most of the countries are following, and they have the different standard, different logos are there, So this is the some standard in Hong Kong, India, Australia, New Zealand, Russia, Germany, European, and then the Sweden have different, that one. And then there is a what you call that's the North America, and then the Brazil. The most of the countries have some standard, Some extent that standard is up to date. Some they are trying to make the more changes on all these things are that one. If you look into the market and economy of this product is very big, If you look into the data of the what called that's the global biodegradable plastic packaging market expected to grow. As per a CAGR is one organization who can do the analysis and all these things, and they say that 18%, from going and reach value of these billions, and now they say that this is going to be a 15 billion by 23, and then they have forecasted that 14% or something they are going. As I saw in my first slide, that multi-billion business, So this business is going to be a multi-billion, not by saying, but the statistical also show that this is available, And when we look into the future of biodegradable packaging, basically in food and beverage, 60%, pharmaceutical 25%, and other use 15%. So most is in the food and beverage in the packaging industry that's needed this one, And trends and impact, one of our UK partners have shared that was the strategy going on to the UK to make a zero plastic waste, So they have a total map here that how they are going to put into the sustainable source and how they are going to consider and all these things. So they have a full channel of the planning in the UK, and they also recently level of trend establishment, how the emergent this technique is going on towards the people perceptions and all these things. So they, and also they done some survey in the UK, and they find out that the people have consumer claim that they are, because as the previous we talked, because when we are talking about the bio-based material, this material is costly compared to the plastic, So the main thing is happening that our awareness, like for example, most of the, like for example, India and others, when we say this is a compostable and biodegradable and I need to charge, people say, no, I don't want, I just want the plastic, So the awareness is also very important, that one. So people need to understand that how we are contributing to the society. What is the impact is going to this plastic material, what we are using, So they done that one. There is a shoppers, they take the interview, them that, and they are ready to pay, So if they are going to ready to pay, then it encourage for you to use the bio-based material, because the bio-based material is not cheap. We need to understand that the bio-based materials, what we are talking here, it's the cost-wise, it's upper than the plastics, So you need to understand that we are contributing towards that one. So these are the some survey they done in the Wales, because the university which we work with, the Bangor University, is in the Wales part of the UK. So they done the survey and globally, and they look on that one. So most of the 1 in 4 Welsh shopper place plastic as a most important global concern, They check with the people, and everybody's are concerned about that one, the global warming and that things. And what's the impact, the beneficial changes that will happen in the real world, creation of new IP, when we are making the new products and all these things, and exploit or use changes in regulation, new standard for assessing the products, what we are talking, that different types of new standards is coming, influence at trade organizations, like for example, all of a sudden you stop to use the plastic. So what happened to that existing industry suffer, and new industry need to come that one. So we need to look onto that angle. And as we are, everybody's talking about that one. So the UN have a different SDG goals, So when we look into that one, these are the different SDG goals we concern in this, that the link to this research. And there are some challenges. Of course, there is some challenge of barrier performance and strength, cost, end of the life infrastructure. These are the some of the challenges we need to overcome from that, And this is the some photograph of our groups, when we get together in UK and Malaysia with all the things. And this is the output of the project, So we started the Fiber Strong one startup company in Malaysia. It's basically we started before the lockdown, but due to lockdown it's not happened. So after the lockdown we established this company, and our target is that what the oil palm pineapple fibers is available, how we can convert them into the biodegradable and sustainable packaging materials. And as you know that the current global problem, so I don't want to go this one, and present global solution, how we can be replace plastics with the biodegradable and sustainable materials and all these things. So this is our product from that, and we have targeting that we can make the water oil resistant, microwave proof and chiller and freeze proof, and can be thrown away together with the food waste. You don't need to segregate these packaging materials. And we have patented this technology, that one in the Malaysia we patented these technologies, and we have also the full plan to how to make, because the existing pulping plant is not suitable for our purpose. So we modified the pulping line flow chart for oil palm based fibers, how we can make it the pulp. And our strength is that one, we have a huge amount of the raw materials available in the Malaysia, and it can be exploited into the different packaging materials. And we have targeted that in the future we will compliances with this 3 standard at least, because we have targeting to the global market. So we need the EN 13432, and also the locally we need the CIRIM eco-labeling schemes. And our impact to the create a new employment opportunities and the empower the local workers in the rural areas, and also we turn agriculture waste into the economical viable product that stimulate local economy, and also attract the foreign investment and reduce the amount of the plastic waste sent to the landfill, because as you know that the Malaysia is previous time dumping station from the Europe and others, it's a dumping there, but now they are very concerned about that one because they have limited landfill spaces there, that one. And this is our partner. So beside me there are one, the Leong, he's looking for the commercial one, and the Amir, he have a very long experience in the packaging industry, and one of the Tariq is my colleague in UPM. So this, we are 4 of the director of this company, and our target that now we have basically plan to roll out into the market, but still we struggle, we are unable to do that one, and we have going on to that one. So we will try to go into that one, the roll into the market, and we have program to build own manufacturing facilities, you know. And this is the team members informations, and this is the what called the, and beside that, because I am a researcher, you know, I do the publications and all these things, but when go to the industry to produce our product, talk about that things, it's very tough, you know. It's not easy job. So we done the pitching, you know, with the different industry for getting a what called as the financial, you know, to support to us, and sometimes even selling our product, you know. So we done the role, and it's sometimes it's a tiring job, but it's the interesting things to learn from that one. So I also done with a lot of companies. We went them, and this is the some of the photos I'm sharing with the different companies. We show them our products and all these things. This is another discussion going with the SIPCO and back renewable energy in Malaysia. Also we done with the Grant March Private Limited, and also we done with the Sime Derby. Sime Derby is one of the big plantation, means the owner of the palm oil plantation in Malaysia. So it's still we are unable to do, but I try to pursue them that how you can utilize your biomass, and it's one of your byproduct business, you know. You can go that one. So these are the some of the staff, but unable to talk with the top management, you know. And before that I already left that one, but still we are looking forward to that one. Maybe we get the time to talk with the top management and convince them to use this, you know. And this is another, we also involve some final year project student, you know, to design the some of the product on the pulp molding. So this is the 3 student who is the final year project from the what called that there is a department of the product design under the architect in the faculty of architect and design. So we assign them, and they produce there into the exhibitions and all these things, you know. And this is another, we have nowadays working to utilize the coffee waste. So we have also designed with the Zeus Espresso is one of the coffee chain in Malaysia. I don't know other places available or not. We also done with one of the footprint company. This is worldwide company who is in the pulp molding, you know, basically. So they recently established company in Malaysia, and they're very interested to collaborate with us. And we already done 1 year discussion and all these things. And when we ask 1 million ringgit to them, they say it's a peanut for us. But lastly, we don't receive the peanut, you know. And this is another company, Euro Atlantic company. He is that company who supply the plastic tray to all hypermarket. So we have already talked, everything happened, and then last they came to sign the contract with us. They say, oh, you are not manufacturing, so you are third party, we cannot sign. So there are a lot of up and downs going on, you know, with the things. And beside that, we have to concentrate on our student research, and beside this headache, you know. But it's a good experience. So dealing with that one, and this project also give me lot of recognizations, you know, into the university level and outside. So I get the award from the Prime Minister Advisor from Malaysia, you know, that time when we get the project. And also my Vice Chancellor have given me to bring the highest amount of international grant, you know, to the UPM. And also I get the excellent academic awards and some medals, gold medals in show and all these things by the Deputy Vice Chancellor of Industry, you know. And this is the some awards I'm sharing to you, you know, that one. And this is the some medals we in the Malaysian Technological Expo, we went there. And lastly, I want to acknowledge all my co-researchers and the PhD master student, all the funding agency, especially to the UK and Malaysia industrial and academic project partners for achieving these things through. Without them, it's very difficult for us to achieve these things. And lastly, thank you to all of you. And if anything, I have the email ID I put into the initial of my presentations. So if you want to contact me, you can email me, and then we can further discuss on that one. Thank you so much.
Okay, we are running a short of time and equation with the professors.
Thank you. Thank you so much. Basically, the gassing, nothing going to be happen that one, Basically, what we are doing, we just use the fibers, in this one. And we, of course, the pulping process, of course, you use the energy and all these things. And it can create the certain type of the pollutions, that one. And the main thing is only the problem with this one, because the oil palm fiber is a tough fibers, tough fiber. So you need to make it soft. So we done the two parallel, like in Malaysia, we done the pulping by using alkali. And in the UK, they done with the mechanical pulping. So they don't use any chemical. But when we use the alkali chemicals, we need to drain out, we need to do the water treatments, and all these things are there, So of course, there is not no any green emissions or anything from this product, little bit, as I say, the water, if you use alkali, but if you go with the mechanical pulping, then there is no issue of that one. And this is just an example. You can use with the different agriculture waste, So this is the one of the example how that oil palm fiber can be utilized. It can be used the dead palm fiber, it can be used the other fiber. But we need to understand which fiber you are going to use, because the things are that one, the pulping is very important here. If your pulp is not going to consist of the certain types of the fiber size is there, you cannot form. So that is the technique here. The main technique is the pulping. So you need to analyze the pulping, and you have to do the classifier. You must have one machine, it's called the fiber classifier. So they can give you the idea that what type of fiber size is available in your pulp. So there is a combination of long fiber, short fiber, then you are able to form. Otherwise, you cannot get that mold, Molding cannot be formed from that thing. So main thing, you need to be expert on the person who have a little bit idea on the pulping. Because we done lot of trial, because it's a long project, So we done the several trial. One time we run it, that failed. We done the second time. Similar with the extruder, different types of formulation. We use the PBS, that one, and we have a different formulation. Then we mix, because the PBS is costly as a biopolymer. So we mix with the starch. We done little bit play, lot, and then after we get the final formulation, then we go with the trial. So this is what we are getting. This is a lot of background research is there, So this is just I show you the output only.
Thank you, Professor. I think if there is any question, like you can discuss with the professor in the break time.
Yeah, you can personally meet me, or you can email if you have no time at this moment. Okay, thank you so much.
Okay.
So thank you very much for the third keynote speaker, Dr. Javed, and also Dr. Krit for introduction. Next, I will now cordially invite Dr. Indra, research scientist of, and I invite Dr. Manoj, research scientist of KUTNB, to introduce about our last keynote speaker of the conference.
Thank you, Ms. Hani. Good morning to all of you. I now introduce our last keynote speaker, Professor Dr. Jyotish Kumar from Alliance University, India, to deliver his keynote speech on waste plant fiber for advanced application. Dr. Jyotish Kumar Parmeswaran Pillai is currently an associate professor at Alliance University, Bangalore. He received his PhD in chemistry, polymer science and technology from Mahatma Gandhi University, Kolkata, India. He has such as Lebanese Institute of Polymer Research, that's in Germany, Catholic University of Leuven, Belgium, University of Potsdam, Germany, etc. He is a prolific editor and researcher who has published or edited more than 40 books, published 160 high-quality international research articles, and 100 book chapters with an H index of 43. He is a frequent keynote speaker and a consultant for multiple organizations internationally. He has received numerous prestigious awards, including the DST Inspire Faculty Award from Government of India. I now hand over the session to our Professor Dr. Jyotis Kumar. Over to you, Professor.
So thanks for the kind introduction. First of all, I thank Professor Suchar and Professor Sanjay for giving this opportunity. So today my lecture on plant fiber for industrial applications. So initially I thought it is waste plant fiber, then I changed it to plant fiber for industrial application. So I will talk about some of the basics of plant fibers in agriculture. So as you can see, we have different fibers. I mean, you can see we have different fibers available across Asia, and these are some of the fibers. We have fir fiber, we have banana fiber, we have sugarcane fiber, then our pineapple fiber. All these are available in southern part of India, and we have a hemp fiber that is available in the northern part. Then we have cotton fiber. So different fibers are available in India, but I mean not only in India, across Asia. But unfortunately, we are not able to utilize them properly. But if you look at the history of, the fibers, you can see the flax fiber is one of the first fiber used by mankind, approximately some 30,000 years back from Georgia. I mean, if you look at the archaeological evidences, then you can see we have, the primitive man used flax fibers approximately some 30,000 years before. And then you can see, some evidences from Switzerland, some approximately some 9,000 years back. Again, they have used flax fibers for, difference of applications, including clothing, including, climbing, etc. And then coming to Egypt, if you can see here, again some 6,500 years before, approximately 7,000 years before, it was discovered that they have used, Egyptian people, primitive men used, flax fibers for difference of applications, hunting, fishing, climbing, carrying, clothing, etc. So that means people used, the primitive men used flax, fibers, plant fibers, even before metallurgy and even before pottery making. And if you come to India, you can see, this is actually a hut that we call Buhanga, and this actually I have taken this photograph from Gujarat. So in such Gujarat in India, one could see this kind of building, hut, and this is environmental friendly. And if you look at this Buhanga, this is completely environmental friendly, and this is made up of this is made up of cow dung, then bamboo, then grass, and then soil. So this is completely environmental friendly. So that is the advantage of Buhanga. And other than that, if you look at this Buhanga, they have temperature insulation property, soundproofing, and also fire resistance. Not only that, they can withstand earthquakes as well as storms. And if you look at some of these Buhangas, they were more than 200 years old. So that is the advantage of this kind of Buhanga, and they are completely environmental friendly. And if the state government Gujarat, they are encouraging village people to construct this kind of Buhanga more. So till the beginning of 20th century, people were using plant fibers for different of applications. But once we have the invention of synthetic fibers, for example, nylon, acrylic, nylon you can see, nylon, nylon, then acrylic, we have rayon, we have polyester, all these are synthetic fibers. Then comes the diminishing of plant fibers in clothing industry. So till beginning of 20th century, we have used cotton, we have used wool, we have used linen, we have used silk for for clothing applications. But again, with the invention of these synthetic fibers, the use of natural fibers is diminished, especially in clothing. And if you look at the composite industry, so with the invention of carbon fiber, with the invention of glass fiber, Kevlar, boron, etc. So they are all have very high strength, very high modulus, lightweight, good compatibility with the polymer. So we are using these materials for composite industry for the last 50 years. And yes, of course, these materials is Kevlar, then boron, carbon, glass, etc. have significant advantage, especially in composite industry because of their high modulus, because of their strength, etc. But if you look at the after use of these materials, we need to landfill it. So that is a big issue. It is not. If you look at the synthetic fibers, you can see it is non-biodegradable. It is highly toxic, and we cannot recycle. And some recycling is actually going on approximately 2%. The synthetic fibers are replaced, but 98% of the fibers are actually landfill. And also these composite materials are actually landfill and finally end up in specific ocean. And so that is actually a big problem that human beings are facing, because we cannot recycle. Approximately 2% is recycled and rest is landfill. So that's why we are interested with plant fibers, because as of course we have synthetic fibers with lots of advantages, but they are toxic, they are non-biodegradable, and we are landfilling it. So that's why we are interested. And also we have emission of carbon dioxide, global warming. So we need to reduce the emission of carbon dioxide, greenhouse gases. So that is why we are interested with plant fibers. If you look at some of the advantages of plant fibers here, they are highly sustainable, they are environment friendly. As you can see here, they are biodegradable. They are, low environmental impact during the production, less carbon dioxide, then easy handling. So these are some of the advantages of plant fibers. And that's why we are interested with plant fibers. But even though we have lots of advantages for these plant fibers, we are still using synthetic fibers. In India we have Vande Bharat Express, we are using glass fibers for making Vande Bharat Express. But we can use, from my personal point of view, we can use plant fibers for those kind of applications. Now the problem is, even though we have many advantages for these plant fibers over, synthetic fibers, the problem is, we have the poor awareness of the importance of natural fibers. And the farmers usually what they do is, after harvesting, they used to burn the plant fibers. So we have issues in Delhi because we have smog issues because of burning of the fibers, and and also we have emission of greenhouse gases, and you can see we have loss of nutrients in the soil, and also we have loss of soil property. These are some of the disadvantages of burning natural fibers. So anyway, you can see we have poor awareness on the importance of natural fiber, and then we have limited knowledge. That is the other reason. And we have the poor supply of natural fibers. Even though we have across the Southeast Asian countries, we are rich in natural fibers, we have poor supply of natural fibers. That is one of the reasons why we are struggling to make use of these natural fibers. And also the companies are reluctant in using plant fibers for advanced composites. So of course in Europe now companies are using natural fiber for automobile industry, and also in aerospace application they are using natural fibers. But in other countries, nowhere, the plant fibers are, using, because of the reluctance of using plant fibers in advanced composites. And also the lack of standard processing methods. So these are some of the reasons why we are not using natural fibers instead of, synthetic fibers. Poor awareness, limited knowledge, poor supply of natural fiber, the reluctance of using plant fibers for advanced composites, and lack of standard processing methods. These are the problems that are responsible why we are not at all interested with plant fibers. I have put some other reasons also here. You can see moisture absorption is there, then inferior properties when compared to that of synthetic fibers, and also the lack of standard processing method, lack of post-processing approaches, etc. Different reasons are there. But most of these issues, the inferior strength, moisture absorption, all this we can overcome by making use of some chemical treatments. Now if you look at the classification of plant fibers, we can classify plant fibers based on the plant source, and also we can classify based on the parts from which plant fibers are extracted. So based on the plant source, we have two different types of plant fibers, and you can see we have primary plant fibers and we have secondary plant fibers. So primary plant fibers means we are cultivating plants for fiber only. For example, hemp, you can see hemp here, you can see flax here, you can see quinoa here. So all these fibers are primary plant fibers because we are cultivating them only for fibers. And then we have secondary fibers. For example, banana is a secondary fiber, pineapple is a secondary fiber, because we are cultivating these plants for fruit, but we can also use their fiber for advanced application. That's actually what we call secondary fibers. So we have two different types of fibers. We have primary as well as secondary fibers. Now based on the parts from which the fibers are extracted, we can classify them into bast fibers, we have leaf fibers, we have fruit fibers, and we have stalk fibers. So we have examples for bast fibers, bast or stem fibers. We have flax, hemp, quinoa, jute. All these are examples for bast fibers. And we also have leaf fibers. We have pineapple, we have banana. All these are leaf fibers. Then we also have fruit fibers. Coir is a fruit fiber. Then cotton is a fruit fiber, and then we have stalk fibers, we have bamboo, we have rice straw, bagasse. All these are examples for stalk fibers. So if we look at these fibers, these bast fibers, leaf fibers, fruit fibers, stalk fibers, we are interested with the bast fibers as well as leaf fibers because the cellulose content in these fibers are more. When compared, in bast fibers we approximately have 70% cellulose content. And in leaf fibers, we approximately have 65% cellulose content. And in fruit fibers, we have approximately 40%. And in stalk fibers, again, we have 30 to 40% cellulose content. We are more interested with the bast as well as leaf fibers because cellulose content here is more. So you can see here in flax, as I already told, we are interested with stem fibers or bast fibers. And also we are interested with leaf fibers for industrial application. This is basically because the cellulose content in bast fibers as well as leaf fibers is approximately 60 to 70%. And you can also see here the properties of plant fibers and their dependence on their composition. You can see here, if the cellulose content is more, means strength is more. And if the cellulose content is more, means the thermal degradation is less. If the cellulose content is more, means biological degradation is less. If the cellulose content is less, means the moisture absorption is less. If the cellulose content is less, means UV degradation is less. So this is the reason why we are interested with the bast fibers as well as leaf fibers for industrial applications when compared to other type of fibers. Now again I have put one cross section of bast fiber as well as leaf fiber. So you can see this is actually hemp fiber, and you can see this is actually the cross section, and just below the skin we have the fiber, and you can see this is the skin, and just that blue color, that this is actually a bundle of fiber, bast fiber. So it is just below the skin, epidermis, and you can also see the cross section of pineapple here. So you can see a schematic also here. This is actually the skin, and just below the skin you can see the fibers here. And there are different methods available to extract these fibers, and I will explain in detail. And you can see we can extract fibers by different approaches. One is dew retting, and then we have water retting, then we have chemical treatment, etc. Different methods are available. You can see we have enzyme retting is there, we have mechanical retting, we have chemical retting. These are the different methodologies we can adopt for the extraction of plant fibers. If you look at dew retting, you can see this is a schematic, the photograph of dew retting. You can see this is all flax fibers. So what farmers do is they cut the plants after harvesting, and they ground these plants in the ground itself, in the farmland itself, and this will work only in moist atmosphere. So dew retting will work only in moist atmosphere. So because of the presence of moisture, because of the presence of sunlight and microorganisms, they cut down or break down the cementing materials that is present in the plant fibers, and finally we can have individual fiber. So this is one approach, that is dew retting. And then another method is water retting. So especially this is actually in dew retting, people, as I already told, this is flax fiber. Flax fiber is widely cultivated in France, and in Belgium there people used to do this approach. And then in water retting in Bangladesh, people are interested with the water retting process like this. So what they do is farmers cut their fiber, and then they soak it in rivers, ponds, or slow streams for 2 weeks, maybe 4 weeks, to remove the cementing material, to separate the individual fiber. So this is the water retting process. And you can see this water retting process, the fiber quality is better than compared to dew retting. So water retting, we have better fibers, and here the fiber quality is not that much good in the case of dew retting. And then we have enzymatic retting. In enzyme retting, we use enzymes. So you can see one photograph here. So this is hemp fiber, and this is alkali treated hemp fiber, and this is enzyme treated hemp fiber, and this is enzyme plus alkali treated hemp fiber. So you can see with the treatment, with the enzyme treatment, we can separate individual fibers. So this is another approach. And then we have mechanical retting. Here people are using hammer mills. You can see this is plant fiber, plants, and then they pass their plant fibers through this hammer mill, and finally we will get very nice fibers. And yes, of course, fiber quality is not that much good like water retting process or enzyme retting, but still it is a fast process. That's why industries are interested in this kind of retting process. And then coming to the last method, that is actually chemical retting, where what researchers do is they put the plant fibers in alkali, in NaOH. So you can see what they do is they put their fiber in NaOH, and they heat it for some time at 100 degrees centigrade, maybe for 1 hour, and then they remove. And during this process, they can remove the lictin, pectin, hemicellulose, wax, etc., and they can have individual fibers. But the problem is, this is a chemical, and it is, not environmental friendly. That is a disadvantage of this methodology. And now coming to the properties of these natural fibers, we can see we have difference of fibers here. And if you look at the properties, most of the the tensile strength is approximately 200 megapascal, And Young's modulus is also very good in gigapascal scale. It is written there. And if you look at the density, it is very less. That's why we are interested with the plant fibers. The density is less, and they have substantially good, good mechanical properties. That's why we are interested to replace natural fibers with the, synthetic fibers. Now there are different approaches one can synthesize plant fiber reinforced composite. So this depends on the application. This also depends on the the fiber length and all. So we do actually, myself and my colleagues, do in our laboratory hand layup methodology, and also one can use thermoforming, compression molding. We have done lots of work with compression molding, resin transfer molding. We have tried with the vacuum assisted resin transfer molding and pultrusion, and then autoclave. We have tried hot pressing, we have tried extrusion, we have tried injection molding and filament winding. All these methodologies we have tried in our laboratory. And yes, of course, it depends on the type of the fiber, and also it depends on the respective application. So these are some of the manufacturing techniques for the manufacture of polymer fiber, plant fiber reinforced polymer composite. So coming to the properties that affecting the plant fiber reinforced composite, yes, of course, metrics. Metrics is, for example, we have polypropylene and polystyrene. You know that polypropylene is a crystalline polymer, and polystyrene is an amorphous polymer. And the glass transition temperature of polystyrene is 100 degrees centigrade, while the melting temperature of polypropylene is 170. So you can use this polypropylene composite till 170, or you can process it at 150, 170. That's fine. But here you cannot process metrics. And also this is, as I already told, this is crystalline, therefore the modulus is quite high, strength is quite high when compared to that of polystyrene. So metrics is very important. And then we have processing type. If you are using fibers, you cannot process, you should process it below 250 degrees centigrade, because above 250 degrees centigrade there is a possibility for degradation. And then the cellulose content, strength of the fiber, modulus of the fiber, hydrophilicity of the fiber, all these are very important, especially in the performance wise of polymer composites. If the cellulose content is more, means it is always good to improve the properties. You can improve the strength, you can improve the stiffness, and as of course you have low moisture absorption. And the hydrophilicity is one of the problem that is associated with the fiber. So in order to overcome the hydrophilicity, we can do some chemical treatment that I will explain in detail in the next slide. And then we have aspect ratio is very important. So we are always interested in high aspect ratio. If the aspect ratio is more, means we will get better tensile strength, impact strength, etc. And fiber content is also very important. So in many cases it was learned that if the fiber content is more, means we have good improvement in tensile strength, then tensile modulus, flexural strength, flexural modulus, impact strength, etc. And even the fiber length. Most of the composite industry is interested with the high fiber length, because if the fiber length is more, means we can the load will be evenly distributed. And this, of course, orientation of the fiber is also important. We are interested with the 0% fiber orientation, unidirectional fiber orientation that will give maximum properties. And this, of course, fiber metrics accretion is also important, and then specimen condition is also important. So as I told, fibers are hydrophilic, so therefore some kind of surface modification is required. And what we do in our laboratory, we do sodium chloride, sodium hydroxide treatment, we do benzoylation, we do acetylation, we do saline treatment, we do KMNO4 treatment, etc. to reduce the OH groups that is present in these fibers, and to improve the compatibility of the fibers with the polymer matrix. And also we can try hybrid composites. So anyway, we also tried with the difference of materials in our laboratory. We tried different fibers. We tried different natural fibers, plant fibers. We tried plant fiber as well as synthetic fibers. So we done lots of work in that to improve the properties. And there's of course lots of application in this area. So automotive industry, as you can see, automotive, body parts we can make in aviation industry, etc. And coming to nanocellulose. So in our laboratory we are interested in nanocellulose. We are interested with macro as well as micro scale plant fibers, but we are also interested in nanocellulose from plant fibers. And you can see this is actually a cross section of plant fiber schematic representation, where you can see we have our nanocellulose here in the cell wall, and you can see we have fibril there in the cell wall, and we have macrofibril, and we have cellulose. So there are different approaches one can extract this nanocellulose from plants, and you can see we have a mechanical method, and we have acid hydrolysis, we have chemical as well as mechanical process, and also we have biological method. So in our laboratory we are more interested with the steam explosion, mechanical method like steam explosion, high pressure homogenation. We also tried ball milling, we also tried fry crushing, and we tried acid hydrolysis. We tried weak acids, we tried strong acids. Weak acids means oxalic acid. We have tried acetic acid, and even we have tried natural weak acids like citric acid, and we tried strong acid like sulfuric acid, phosphoric acid, hydrochloric acid, etc. And we also tried chemomechanical. Here we have two different methods we have simultaneously tried. That means acid hydrolysis as well as high pressure homogenation or steam explosion. And also we can use biological methods. That means we can use difference of bacteria so that we can extract bacteria based cellulose. So these are some of the approaches we can synthesize nanocellulose. This mechanical method is plant based, and this hydrolysis again plant based, and this is chemomechanical, again we can use with plant fibers, and this biological. Yes, of course we can use difference of enzymes, etc. And also you can synthesize certain nanocellulose from bacteria also you can synthesize. So this is actually a schematic representation for the production of cellulose nanofibers as well as cellulose nanocrystals. So if you go with weak acid along with some mechanical treatment, you can have cellulose nanofibers. But on the other hand, if you go with strong acid, you can make cellulose nanocrystals. And this is one of our work we have recently done, and we have used aracanut palm sheath. So this is widely available in our place, and we make a nanocellulose suspension from this material, and by using then we have included zinc oxide nanoflakes in this nanocellulose suspension, and then with the help of vacuum filtration we have synthesized nice cellulose papers, and then we dipped this cellulose paper in stearic acid, and finally we make hydrophobic nanocellulose papers. And you can see this is a schematic representation of the mechanism there, and this is our cellulose, and this is our zinc oxide. You can see there zinc oxide, and then you can also see the stearic acid. And stearic acid form have some esterification reaction with zinc oxide, and zinc oxide form some hydrogen bond with the nanocellulose, and you can see finally we have a hydrophobic cellulose fiber we have synthesized. And you can see the contact angle here. So this is our pristine cellulose paper with a contact angle of approximately 40, and this is because it is hydrophilic. But on the other hand, when we included zinc nanoparticle, you can see the contact angle increases to approximately 80 or approximately 80. And when I dipped our zinc oxide modified CNF in stearic acid, you can see the contact angle increases to 150. That means we have super hydrophobic film we have developed. And you can also see the stress strain curve of our sample. So So this is with the pristine CNF and also with modified CNF. You can see when we, with modified CNF we have very good strength as well as modulus, and you can see this is in dry atmosphere and this is in wet atmosphere. Whether it is in dry atmosphere or in wet atmosphere, we have maximum performance with modified paper. And we also tried biodegradation studies, and you can see our sample is 100% biodegradable after 30 days, and you can see, so it is completely biodegradable, you can see after 30 days, and you can see, so you can see it is hydrophobic with a contact angle of approximately 150. So you can see the water droplets are rolling over the sample there. So basically, the cellulose fibers are hydrophilic, but after this treatment with zinc oxide nanoparticle as well as stearic acid, we have fully hydrophobic surface. And this is our another work where we have done in our laboratory with the support of Dr. Mudin. And you can see we have used a pineapple, and this is actually pineapple based, that we call pineapple pomace. And then we have dried this pineapple pomace, and then we did alkali treatment, and then followed by bleaching, and finally this is our bleached pineapple. And then we did acid hydrolysis with strong acid as well as weak acid, and we have synthesized nanofibers with both these approaches. And finally we make nanopapers, and we learned that the nanopaper that was synthesized with the help of oxalic acid, weak acid, is very good in terms of their mechanical properties. And therefore what we did is we use essential oil, and we incorporate essential oil in our cellulose film. And you can see when we incorporate this cellulose, this essential oil, cinnamon essential oil, we have incorporated cinnamon essential oil in our film, cellulose nanofilm. And then when we have incorporated this cinnamon essential oil, you can see we have some plasticizing effect, and with a good water vapor transmission rate is reduced. You can see water vapor transmission rate is reduced when we incorporate this cinnamon essential oil, and also you can see carbon dioxide transmission rate is also reduced when we have incorporated cinnamon essential oil. And we also studied the antibacterial effect of this material, and you can see we have a very nice antibacterial effect. You can see the zone of inhibition here, and you can see it there. And we have very good antibacterial properties against both the gram-positive as well as gram-negative bacteria. And we have used this film for packaging our coriander leaf, and you can see this coriander leaf remain as such for 15 days in refrigerator, so we can improve the shelf life of this material. This is basically because we can reduce the water vapor transmission rate, and also we could reduce the oxygen transmission rate. That's why we could increase the shelf life by 15 days here. And this is another work where cotton linders were mixed with ionic liquid, and nanocellulose have been made, and that is actually used for composite film. And then this can be used for for oil packaging. So this kind of applications we can do with nanocellulose. And then this is another work with polypropylene nanocellulose foam. So usually we have a PP foam is like that, the bubbles are quite large in size. So when you incorporate this nanocellulose, you can reduce the bubble size because of the nucleating effect, and also you can improve the performance of this material. So that is again you can use nanocellulose for difference of application. And yes, of course we have difference of application. My team is working on now capturing carbon dioxide with the help of nanocellulose. The work is going on, and we are working on food packaging similar to here we are interested with making pulp with a difference of material, and we are trying to make food packaging like this. And we have done lots of work with water waste treatment, and we have done lots of work in textile. And yes, of course, there are so many different of other applications also. My team is working strongly on this area, and we have published more than 100 papers in cellulose nanofibers over the last 15 years. And finally, I would like to thank all my collaborators, Sir Chad, President of KMUTNB, my supervisor, Professor Jones, with some 10-15 years back, but still we have very nice interaction and collaboration. And Professor Sanjay, my colleague, and Dr. Nidin, which always supported me, and my professor, Professor Jürgen Piontek, Professor Paula Montenegro from Belgium, Professor Joachim Kurtz from Germany, and my colleagues all are sitting here, Professor Sedil, many others have supported me, and I would like to thank all my colleagues and students for their support over the last 15 years. That's the reason why I could publish quite a lot in this area. And thank you very much for your patient hearing.
Thank you, Professor, for an insight talk on waste plant fiber for advanced application. Once again, thank you, Professor. Thank you.
As we are running short of time, if you are having any discussions or questions, you can discuss with the professor in the break time. Thank you, Professor.
Thank you very much, Dr. Manoj, and also Dr. Yotish Kumar for your insights. I now cordially invite Dr. Indran, the research scientist of KMUTNB, for delivering the vote of thanks.
Myself, Dr. Indran, on behalf of our university and all the committee members of EFPM 24, I would like to express my sincere thanks to our beloved chairman, beloved president, director of Technopark, and vice presidents of our university. Thank you. I extend my wholehearted thanks to all the keynote speakers and invited speakers for delivering a talk at the ESPM 24 conference. Thank you. I thankful to all the participants of various countries who have been registered for EFPM 24. Thank you. At this juncture, I wish to thank all the Technopark team, ICC team, AED team, STRI team, and TGGS team for their constant support in conducting this conference. Also, I would like to express my gratitude to all the academic committee, advisory committee, and scientific committee members for this conference. I would like to thank all the organizing committee members, technical committee members, and all our NCRT members for their constant support and involvement. I want to thank all the media members for their support and extensive coverage for this event. I hope this conference will be informative and you will enjoy all the upcoming sessions. Thank you one and all, and we expect your presence in our future events of KMUTNB. Thank you.
Thank you very much, Dr. Indran. We take this special occasion to announce about our next international symposium on the advanced manufacturing for polymeric materials, the EFPM 24, through a short video. Please enjoy. for this part, now I request
for the first with the conference chair, the conference co-chair, and the conveners, along with the vice president of KMUTNB and the keynote speakers on the stage to take the group pictures together, please, for the closing ceremony, sir. And I would add more of the team of the conference organizer committee to join the prestige guests on the stage for the group picture, please. Keynote speakers and the vice president, please remain on the stage. And for the third picture, may I ask the conference, excuse me, may I ask the NCR group members to join with the guests on the stage for the picture, please? Thank you very much. And for the first morning session, where I come towards the break time, we will now have the lunch break, and we will join again in the invited talk by 12:50 p.m. at the fourth floor on the same building. Also, as for the afternoon session, we'll have parallel sessions in different rooms, but the coffee and the beverages will be stay in the same room in the back behind the stage. That would be the coffee room. So if you feel thirsty and you want a break, you can come by to this room again. And thank you very much for your participation for the morning session, and please enjoy the celebration time, and see you again on the evening session with the celebration and the parties. Thank you very much. The Techno Park team for taking the pictures. Thank you.